Whether perceived as the rudimentary red dot in the sky by our ancestors, or the planet traversed by contemporary robots in their adventures, Mars consistently evokes a sense of exhilaration and intrigue. Once seen as Earth's sister planet and a potential habitat for extraterrestrial life, Mars has frequently been the focus of exaggerated speculation and limited information. Recent probes have unveiled the planet's authentic characteristics, debunking numerous ancient myths. Recent discoveries have introduced unexpected elements, rendering Mars an even more captivating location than previously thought. What insights have we gained from the Mars probes? Mars is an intricate and expansive realm with an extensive past like Earth. This book will substantiate these principles, exploring the essence of modern planetary science while addressing its ambiguities and sporadic certainties. We present a wide range of photographs, including some previously unpublished ones. While Mars is a captivating location, a book on it should not simply be a photographic collection. The photographs will serve as indicators as we unveil this new universe, which, despite having numerous parallels on our planet, is distinctly extraterrestrial. Let us explore Mars's distinctive characteristics. Imagine being at the foot of Olympus Mons, the largest volcano in the solar system, rising over 20,000 meters. Subsequently, envision the polar glaciers composed of numerous fine layers, which serve as evidence of historical climate variations. The vast plains exhibit the scars of catastrophic flooding, while peculiar dunes narrate the tale of the winds that formed them. These are but a few distinctive characteristics that render Mars a planet of perpetual intrigue. Envision a day spent on Mars. As dawn arrives, nocturnal frost yields to mists and fogs that dissipate, unveiling the orange sky. During the hottest period of the day, dust devils traverse the surface. A little irregularly shaped moon traverses the sky for hours at twilight. Will a worldwide dust storm envelop the planet tomorrow, as it occasionally does during winter? Beyond its stunning landscapes, Mars offers a new realm for comprehension and unveils the planet's mechanisms. Essential inquiries encompass comprehending Mars's formation, the reasons for its divergent evolution from Earth, and the insights its geological features provide in its history. Is it possible that life existed there? Is it now present there? What processes currently influence Mars? These crucial elements render understanding Mars essential to grasping our origins. Among all the planets in the solar system, Mars bears the closest resemblance to Earth. Geologists, meteorologists, and numerous other scientists have an extensive laboratory to evaluate their understanding of the events occurring on terrestrial planets. Mars possesses the advantage of retaining evidence of its ancient history. Conversely, the Earth does not possess this advantage. Our planet's surface constantly changes. Erosion and plate tectonics have erased the records of 4/5 of Earth's history. Few clues exist regarding the Earth's conditions when the initial microorganisms emerged before living beings' extensive utilization of carbon chemistry. Mars can evoke our history and elucidate the origins of life. Comprehending Mars is tantamount to comprehending our own origins. In our exploration of Mars, we must acknowledge the relentless contributions of several researchers and engineers worldwide. Their shared objective is to realize future Mars missions. Over the past decade, over 10 space probes and their robotic explorers have been dispatched to the Red Planet. The subsequent 20 years will witness additional missions from Earth to Mars. We will dispatch fresh probes and retrieve samples of Martian surface material. Individuals will also do the voyage. The exploration of Mars is a continuous and evolving endeavor that produces novel findings and insights. This video series presents a comprehensive overview of our existing understanding of Mars, enhanced by the extensive imagery and findings from Mars Express, the inaugural European probe, and NASA's robotic geologists, the tireless Mars exploration rovers. Before comprehensively analyzing a planet's geophysical evolution, scientists must have a temporal framework to categorize the observable formations. What methods can we employ to date Martian terrains without surface samples? The solution resides in quantifying craters created over extended durations by incoming meteorites. All dates for geological structures referenced in this book are derived using this premise. Mars underwent incessant meteoritic bombardment early after its formation 4.5 billion years ago. The intensity persisted until 3.8 billion years ago. This process gradually declined as the number and size of impact is reduced, stabilizing during the last billion years. Geologists can establish a relative chronology by assessing the density of craters on the surface per unit area. This is feasible due to the reduced frequency of hits over time. The Southern Hemisphere's extensively cratered plateau, frequently referenced particularly in Part 2, contains numerous craters of significant diameter. Therefore, any gently cratered surface, like the plains of the Northern Hemisphere, must precede it. Nonetheless, enumerating craters provides just the comparative age of one location relative to another. Although the Southern High Plateau is indisputably older than the Northern Plains, determining its precise age necessitates a surface sample from Mars to assess its radioactivity for dating purposes. Future space missions will execute this, despite the infeasibility of retrieving the valuable samples. Simultaneously, the Apollo astronauts' retrieval of lunar samples forces planetologists to employ a shortcut method. Our natural satellite has a cratering curve. The lunar samples calibrate this curve by replacing relative dating with absolute dating. Researchers who study Mars have been able to make accurate predictions about the ages of different areas on the planet by using samples from the Moon and adding correction factors that take into account things like Mars' position about the Sun, its gravity, and its atmosphere, among other things. Since we don't have a better method, this extrapolation works well enough for our purposes, even though there are some small differences in the exact estimates, depending on the values given to the adjustments and the models used. The history of Mars commences in the obscurity of the past, during a period when nearly none of the solar system as we recognize it existed. Not even the Sun. However, the cosmos was already ancient, perhaps 10 billion years old, constituting 2/3 of its current age. All the elements eventually forming the Sun, Mars, Earth, and life forms lingered in suspension as gas and dust. The solar system abruptly appeared on the cosmic timescale over millions of years. Subsequent events would irrevocably shape the fate of the Crimson Planet. Before Mars and the other celestial bodies, what is the source of the material that constitutes the solar system's planets? Like the other terrestrial planets, Mercury, Venus, and Earth, Mars primarily comprises heavy chemical components, including oxygen, magnesium, silicon, and iron. The Big Bang, the singularity signified the universe's inception approximately 13.7 billion years ago, did not generate these atoms. This primordial explosion generated solely the lightest elements, including hydrogen, helium, lithium, and deuterium. What is the origin of the elements that create planets? An early concept posited that the Sun produced the heavy elements found in planets. This concept is believed to have originated with the Greek philosopher Anaxagoras, 500–428 BC, who asserted that the presence of iron meteorites demonstrated that the Sun was merely a mass of red-hot iron. The Sun consists of hydrogen and helium. Nonetheless, the notion that it supplied the material for planet formation is not entirely implausible, as heavier elements are found within it. Furthermore, they exist in amounts very similar to those found in the primordial meteorites that formed the planets. In the Sun, as in these meteorites, carbon atoms are present in quantities 11 times greater than silicon atoms. Nonetheless, the concept of a solar origin for the planets faces a significant objection. It fails to explain the discrepancy in the abundance of light elements, particularly deuterium, lithium, and boron. At the time of planetary formation, the Sun lacked certain elements due to their consumption during fusion processes, a phenomenon that continues to this day, whereas planetary material does not display this shortfall. Today, our examination of old solar system meteorites enables us to provide a more comprehensive answer to the topic of the genesis of planets. The Sun and its planets derive their heavy elements from the explosions of big stars after their life cycles. As a star reaches the terminal phase of its existence, having converted all its hydrogen into helium, it generates heavier elements. Helium is transmuted into carbon, oxygen, and nitrogen, which evolve into even heavier elements as fusion processes persist. This process culminates in a supernova explosion in sufficiently massive stars, expelling all these components into space. Subsequently, they will engage in the formation of new stars and planets. Approximately 4.52 billion years ago, the Sun commenced its luminosity within a disk of gas and dust. The temperature was sufficiently elevated in proximity for water and other volatile substances to exist in a gaseous state. Only substances with low volatility, such as silicon oxides, magnesium, and metallic elements, could maintain a solid state. Dust particles interacted and bonded to create porous agglomerates around 1 meter in diameter. Subsequently, these entities collided until they formed kilometer-sized planetesimals, the foundational components of future planets. Following a relatively calm infancy, the Sun transitioned into a tumultuous adolescent phase at approximately 10 million years of age. For the first time since their inception, gases and volatile substances reversed direction and began to go backward. The solar wind, a powerful flow of particles emanating from the Sun's corona, propels them outside the solar system. As matter dispersed, water vapor moved toward areas with lower temperatures. Water vapor condenses into ice particles approximately 820 million kilometers from the Sun, which is 5.5 times the current distance between the Earth and the Sun. When the ice combines with dust, it forms a planet tens of times more massive than Earth's current mass. The gravitational field surrounding this gigantic entity attracted substantial amounts of hydrogen, resulting in the formation of Jupiter during a span of less than 10 million years. Saturn required twice the duration to form at a distance from the Sun, about 1,250 million kilometers, where its orbital period was double that of Jupiter. Uranus and Neptune originated under comparable conditions, consuming icy planetesimals at a distance from the Sun exceeding twice that of Saturn. In proximity to the Sun, planetesimals persisted in attracting and colliding with one another. Within 10 million years, embryonic planets developed into the lesser planets of the nascent solar system. Several were comparable in size to Mars, around 7,000 kilometers in diameter. Around 10 resembled Mercury, 5,000 kilometers. And numerous others were analogous in diameter to our Moon, 3,500 kilometers. Between 4.47 and 4.44 billion years ago, the modern part of the solar system's history began. Earth and Venus accumulated the most available material during the final cataclysmic collisions between planets. A planet comparable in size to Mars had collided with Earth. This impact formed the Moon. Subsequently, Jupiter approached the Sun, resulting in Saturn, Uranus, and Neptune receding further away. Since that time, the planets have sustained their current orbits. A chaotic assemblage of planetesimals constituted the terrestrial planets: Mercury, Venus, Earth, and Mars. These planets now display an iron core, encircled by a less dense rocky mantle and topped by an outer crust. This differentiation would not have been possible without the interiors of the primitive planets melting, similar to how things are refined in high-temperature furnaces. In the 1970s, most planetary scientists believed that the process on Mars required 1 billion years. the duration necessary to generate enough heat from the decay of radioactive elements within the planet. Nevertheless, examining Martian meteorites in the 1980s uncovered a much accelerated timeline. These meteorites did not detect adequate quantities of certain siderophilic elements, which exhibit a strong affinity for iron and are present in Mars' core. This supported the notion that iron predominantly transitioned from Mars's crust to its core during the planet's accretion, with the core potentially forming in less than 50 million years, maybe as little as 20 million years. Accretion generated adequate heat on Mars and Earth, Venus and other terrestrial worlds to purify the elements from the primordial mixture within the planetesimals, akin to a blast furnace. Oxygen, carbon and iron oxides react in a blast furnace to produce iron and carbon dioxide. Iron oxides and graphite from carbonaceous chondrite meteorites mix to produce metallic iron and carbon dioxide in a planet's magma. The molten iron descends toward the planet's core, acquiring additional heat. In contrast, refractory oxides, specifically aluminum oxide and calcium oxide, ascend to the top, forming a layer known as the primary crust. What is the size of Mars's core? What comprises its composition? We have not yet directly measured the depth of Mars's core mantle border. We can learn more by comparing meteorites thought to have a similar makeup to planetesimals, like the carbonaceous chondrite that fell near Ivuna in Tanzania in 1938, with those that contain pieces of Mars' crust, like the Chassigny meteorite. The core of Mars, approximately 1,500–1,900 kilometers in diameter, almost half the planet's diameter, is likely comprised of 70–80% iron and some nickel and sulfur. We can invoke various reasons to explain the evolutionary differences among the 4 terrestrial planets. Factors include starting size, the history of cataclysmic cratering, and the mechanisms of internal heat dissipation. After the accretion phase, around 4.45 billion years ago, Mars was half the size of Venus or Earth and roughly 10 times less massive. In multiple respects, this distinction would be crucial for the amount of energy accumulated within the planets. The gravitational acceleration on planetesimals directly correlates with a planet's mass, leading to stronger impacts as accretion progresses. Moreover, the larger the planet, the greater the concentration of radioactive elements. Massive planets also keep heat in better because their increased gravity makes their atmospheres denser, which keeps thermal radiation out and stops energy from escaping. This explains why, from the outset, the 2 smaller celestial bodies, Mercury and the Moon, underwent cooling more rapidly. Mars represents a transitional phase between the 2 minor celestial bodies and the 2 larger ones, Earth and Venus. The stochastic occurrence of cataclysmic meteorite impacts significantly influenced the internal evolution of planets. The Earth's mantle absorbed most materials and energy from the cataclysmic impact that formed the Moon approximately 4.48 billion years ago. Contrast this with Mercury, which lost most of its mantle due to a separate impact. After the period of material and gravitational energy absorption, the planets emitted a portion of their internal heat, encompassing the gradual release of heat from the radioactivity of the rocks. Which processes were involved? A solid, rigid planet conducts heat thermally toward its surface. This mechanism produces heat loss proportional to the planet's surface area, whereas heat retention is proportional to its volume. A larger planet will dissipate comparatively less energy than a smaller one. This model, however, does not account for the thickness of the insulating surface layers, volcanic activity, or material displacement inside the mantle. Within the ostensibly solid mantle, over geological time, the heated rocks undergo deformation, allowing material from the depths, which is hot and less dense, to ascend to the top, where it subsequently cools. This mechanism, termed convection, is significantly more efficient than conduction in the movement and dissipation of heat. Earth has robust convection, nearly reaching the surface at mid-oceanic ridges, whereas mantle convection has likely halted in the Moon and Mercury. Mars possesses a mantle sufficiently heated to facilitate mild convection, particularly beneath its big volcanoes, where partial melting zones have produced volcanism over the past 100 million years. On the morning of October 3, 1815, the community of Chassigny in eastern France was alarmed by unexpected detonations. A stone had descended from the sky nearby. This 4-kilogram meteorite, which appears to originate directly from a volcanic eruption, has captivated generations of researchers. About 30 meteorites of the Chassigny type, out of the tens of thousands discovered on Earth, fit this classification. We named the SNC meteorites after the locations of their initial discoveries: Chagoti in India, Nakhla in Egypt, and Chassigny in France. It was not until the 1980s that the Martian origin of these meteorites was conclusively established. They are defined by their isotopic oxygen composition. Various isotopes of oxygen exist. Researchers have identified its nucleus in Antarctica and subsequently dated it in a laboratory setting. Researchers have prominently discovered numerous Martian meteorites like EETA 79001 on the Antarctic ice. Geochemists utilize the radioactive decay of potassium-40 to argon-40 to ascertain the origins of materials, particularly those that have crystallized from magma. The argon from the decay of potassium-40 can dissipate once the rock becomes molten. Once it has formed, the argon consolidates within the rock. You can calculate the crystallization time by comparing potassium and argon isotopes to their initial amounts in the Martian atmosphere. For EETA 79001, the age is 180 million years. Consequently, it is a relatively recent rock in the planet's age. What led scientists to ascertain that SNC meteorites are of Martian origin? Dating and research indicated that they were formerly part of a singular, distant parent body sufficiently large to have generated magma and volcanism. Was it Mars? Venus? Was an old planet obliterated during the solar system's formation? A massive asteroid impact certainly expelled the SNCs into space, but we have only been able to contemplate today's planets lately. The meteorite ETA 79001 provided the most compelling evidence of a Martian origin. Antarctica acquired this item in 1980. Enclosed within it were gas bubbles encapsulated in dark specks of basaltic glass. The significant impact that detached the rock from its planet resulted in the formation of the glass. In 1976, the Viking landers conducted in situ analyses of these gaseous inclusions and determined that their composition closely resembled Mars's atmosphere. Consequently, numerous scholars regard SNC meteorites as authentic remnants of the red planet and indicators of its genesis. Mars, Earth, and Venus possess atmospheres of nitrogen, oxygen, carbon dioxide, water vapor, and trace gases, including helium, argon, neon, krypton, and xenon. The distinct atmospheres are characterized by the respective proportions of various gases and global pressures. The atmospheric pressure on the surface of Mars is between 100 and 150 times lower than that of Earth, which itself has an atmospheric pressure 90 times lower than Venus. Planetologists have to do a lot of research to figure out what the atmospheres of planets were like in the beginning. The chemical and physical interactions of volatile elements, the solid crust, the liquid seas, and volcanic activity have greatly changed the compositions. Your role in this process is essential. By excluding elements that make up modern atmospheres from the analysis framework, it is possible to find atmospheric components that have not changed in 4 billion years. Oxygen, nitrogen, and carbon generate carbonates and nitrates integrated into the crust. Deuterium and hydrogen may result from the decomposition of water in oceans and ice deposits. Only the noble gases and their isotopes, atoms of the same chemical element that vary in neutron count and mass remain. These gases are chemically inert, thus their designation as inert gases. In 1976, the Viking probes made a notable finding by measuring these rare gases, constituting a little over 1.6% of Mars' atmosphere. Scientists learned a lot about the history and makeup of Mars' atmosphere from this discovery, especially about how common argon-40 is, an isotope made when rocks break down potassium-40 radioactively, and how little neon, krypton, and xenon are. The creation and history of the Martian atmosphere are further complicated by the planet's low gravity, the absence of a magnetic field, and the currently indeterminate history of volcanic activity. The loss of the majority of the primordial atmosphere can be attributed to these two factors: meteoritic strikes and the influence of the solar wind. The original volume of water on Mars may have exceeded that of Earth's oceans. We now know that during the first phase of accretion, when parts of the core and mantle were formed, the process moved forward with the arrival of planetesimals high in volatile elements and water, making up to 10% of their mass. Analyses indicate that meteorites from Mars constitute 50% of the planet. A significant portion of the water has undoubtedly vanished. However, some persist in the crust as ice and within the planet's mantle. The current quantity is a subject of contention. In the initial 700 million years of their formation, the solar system's planets experienced a period of severe bombardment by asteroids and small celestial bodies that had not engaged in planetary accretion and were displaced from their orbits by the gravitational pull of the giant planets. The peak period of this bombardment transpired approximately 3.8 billion years ago, coinciding with the swift and conclusive migration of these colossal planets. In contrast to Earth, Mars retains the remnants of that event across over 50% of its surface. Craters, varying in diameter from several meters to several hundred kilometers, predominantly populate the southern hemisphere of Mars, the creation of an impact crater. A body measuring merely a few hundred meters in diameter colliding with the Martian surface at a speed of 15 kilometers would release an energy release comparable to several hundred megatons. The Hiroshima bomb's yield was 13 kilotons. An impact of this magnitude can expel chunks of the planet's surface and portions of the atmosphere into space. The residual atmosphere may be obscured by a deluge of debris and dust clouds. During the impact, pressures several thousand times greater than those of the Earth's atmosphere and temperatures reaching several thousand degrees result in the liquefaction, vitrification, and even vaporization of materials. Significant fractures arise inside the subsurface material. The impact creates a compression and stress relaxation wave that causes the rocks below to quickly decompress. This is what causes the crater to form. The excavation phase ejects material along the crater's periphery, which is only 1/100th of a second post-impact. A gradual process commences as the material reconfigures within the cavity. A center peak or ring develops within hours or days following the original impact. The ejector, comprising material expelled from the crater upon impact, some in a molten state, distributes radially around the crater. Impact craters have a morphology that varies with size. The smallest craters, under 20 kilometers in diameter, are bowl-shaped, but the floors of larger craters appear filled and may feature peaks or rings at their centers. Mars is unique because its geography is not symmetrical. The southern and northern hemispheres are about 5 kilometers apart in elevation, and each area has unique geological formations. The southern hemisphere's high plateau is ancient and extensively cratered, whereas the northern plains exhibit a more modern surface with relatively few craters. There is a transitional zone between the two areas with many buttes, single hills with steep sides, and flat tops. This shows that the elevated plateau has been worn down a lot. The boundary of the plateau is indistinct and diminishes into little buttes at approximately 45° N. The origin of this dissymmetry is a topic of vigorous discussion and continuous investigation. We are exploring two study approaches. One suggests an internal geological origin, while the other proposes an external origin associated with cataclysmic catastrophes. Could the dissymmetry arise from asymmetrical convection inside the mantle, resulting in a variation in thickness throughout Mars's crust? The alterations in the trajectories of circling spacecraft enabled scientists to assess the planet's gravitational field fluctuations. These data indicate the crust's thickness and the existence of any subsurface abnormalities resulting from mantle convection. What were the findings of the study? When the Earth's gravitational field changes, it shows that the crust is 40 kilometers thick in the north and 70 kilometers thick in the south. This difference isn't likely caused by uneven convection in the mantle. In the transitional zone between the plateau and the plains, the crust does not display the anticipated differences in thickness. The external hypothesis. Several meteoritic impacts may have attenuated the Northern Hemisphere's crust. New pictures from subsurface sounding radars and studies of gravitational anomalies show that impact sites are buried under thick layers of sediment. Sediments currently obscure the cratered surface, which formed simultaneously with the southern plateau. Subsequently, several kilometers of robust material deposits, resulting from the erosion of the crater-laden high plateau, enveloped it. We do not yet completely comprehend why the Northern Hemisphere initially saw the most significant repercussions. In 1997, Mars Global Surveyor, MGS, was the inaugural spacecraft to traverse Mars at exceptionally low altitudes. One of its mission objectives was to study the ionosphere's magnetic field, the atmospheric layer ionized by ultraviolet radiation and solar wind. The magnetometer engaged upon MGS's arrival at Mars. As anticipated, the magnetic field exhibited a peak as the probe traversed the ionosphere. Nevertheless, to everyone's astonishment, values rose once more during some low passes over the planet's most ancient terrains. MGS identified the relics of an old and once potent magnetic field capable of magnetizing the surface. It was previously believed that Mars lacked such a field. Planetologists now face questions about the origin of this field and the reasons behind its disappearance. Movements within the iron core, fluid, and a potent conductor of electricity generate magnetic fields on terrestrial planets. We do not completely comprehend the precise mechanism that generates such fields. Convection in the liquid core, characterized by the ascent of hot iron from the center to the mantle border for cooling and subsequent descent, is believed to produce an electric current. This generates a magnetic field, the dynamo effect. What is the origin of electric current? It appears that randomly generated micromagnetic fields within this medium produce electric current, resulting in a global magnetic field. Following the accretion phase, approximately 4.45 billion years ago, Mars possessed a sufficiently heated liquid core to facilitate convection and produce a magnetic field. The core presumably cooled rapidly, and several hundred million years later, at most 500 million, the remaining heat was inadequate to initiate convection. Subsequently, conduction, see pages 88 to 90, commenced, and as convection halted, the Martian dynamo engaged. Today, Mars' crust has a residual magnetic memory from the active dynamo. Scientists can only estimate when the dynamo ceased functioning by dating samples from the cratered terrains of the southern region. Two diminutive natural satellites traverse their orbits in opposing orientations in the Martian atmosphere. Phobos, the bigger of the two, has dimensions of 26.8, 22.4, x 18.4 kilometers, and ascends in the west twice each day. Deimos, 15.0, x 12.2, x 10.4 kilometers, ascends on the eastern horizon every 5.5 days. From the surface of Mars, their apparent diameters are approximately 3 times and 17 times smaller than those of the Moon, as observed from Earth. In 1989, the Soviet probe Phobos 2 captured images of Phobos as it neared Mars. Prematurely lost, the Phobos 2 probe aimed to conduct an in-depth examination of this satellite. The operation entailed positioning a module on Phobos, capable of transitioning in phases owing to its diminished gravitational force. The Russian Space Agency intends to launch a new mission to Phobos, titled Phobos Grunt, to return samples from Phobos to Earth within the next decade. Only partial solar eclipses, previously witnessed on Phobos, can occur on Mars due to the Sun's apparent diameter being 2/3 that of Earth. The dimensions and configurations of Phobos and Deimos indicate that they are asteroids, a theory supported by their comparatively low densities relative to the Moon or Mars. Phobos possesses a density nearly double that of water. Deimos has a density of 1.7, the Moon's is 3.34, and Mars exhibits a density of 3.93. The surfaces of the satellites absorb around 95% of incoming sunlight. They possess this characteristic with specific asteroids that orbit the Sun between Mars and Jupiter, at distances ranging from 3 to 3.5 times that of Earth from the Sun, i.e. 525 million kilometers. If Phobos and Deimos are actually asteroids, we can hypothesize how and when they attained their current positions. Mars must have acquired them, similar to how Jupiter, Saturn, and Neptune have with certain satellites. Nonetheless, this does not yield a solution. Space probes must activate their engines to generate a braking effect and attain orbit. An asteroid must be decelerated for capture to transpire. Multiple models are under evaluation. The initial hypothesis, mirroring the narrative of the Earth and its moon, posits that a celestial body collided with the planet, ejecting debris into orbit, which subsequently reaccreted. Regrettably, this method is improbable for Phobos and Deimos due to their insufficient density. Another model incorporates aerobraking, wherein the body experiences rapid deceleration while traversing a dense atmosphere. An atmosphere was present on Mars during its formation, but solar activity rapidly dissipated it. If this model accurately represents reality, then Phobos and Deimos may be the final remnants of the planetesimals that contributed to the formation of Mars approximately 4.5 to 4.3 billion years ago. The inquiry remains unresolved. Is it possible that an oasis existed where life may have thrived? Our narrative progresses in a world remarkably distinct from the one we already inhabit. Its geological record discloses events from a nascent planet, often subjected to impacts from numerous celestial entities still in orbit around the Sun. On this nascent Mars, temperatures intermittently permit liquid water. Rivers and lakes erode the surface, accumulating sediment. Approximately 3.8 billion years ago, the initial microorganisms originated and evolved on Earth, where environmental conditions were only marginally more conducive than those on Mars. Is it possible that life originated on the Red Planet? In 1972, Mariner 9's identification of unusual valleys resembling desiccated riverbeds was remarkable. Researchers soon discovered analogous fluvial characteristics throughout the 3.8 billion-year-old cratered plateau in the southern hemisphere. Nevertheless, more recent landscapes had less evidence of these valleys. Approximately 3 billion years ago, Mars exhibited conditions conducive to forming river valleys, conditions that have not re-emerged since. Were we genuinely observing evidence of rivers? This documentary series examines various flow characteristics produced by liquid water. 1. Numerous dendritic fluvial valleys, including meandering examples such as Nergal, Nanedi, and Ma'adim, were created over 3.5 billion years ago, perhaps during a period of more temperate climate than the present, as detailed in this section. 2. Significant outflow. These channels are new, with diameters over 100 kilometers. Violent, catastrophic discharges presumably formed these canals at multiple locations throughout Mars's history. However, the climate may not have significantly differed from current observations. Minor remnants of gullies extending several hundred meters seem to originate from a few 100,000 years ago, or perhaps even more recently. Yesterday, in geological terms. Many of these valleys, some extending up to 1,000 kilometers, possess numerous distinct branches with tributaries converging akin to a drainage basin. This distinctly tree-like configuration indicates that the episode S, during which the liquid flowed, persisted for a considerable duration. Planetologists agree that the liquid responsible for shaping the valleys was water. Alternative hypotheses involving lava and liquid carbon dioxide have been proposed but remain unpersuasive. It is hard to compare the valley networks on Mars to those on Earth that are more recent because the Martian networks are so old, and certain features are slowly losing their importance over time. At first, it was thought there weren't as many branches as on Earth. However, new thermal imaging has found many previously undetectable tributaries in systems with densities similar to those on Earth. Numerous inquiries arise. Is a warm and humid atmosphere essential to initiate such flows? Could a frigid Arctic climate have produced a similar effect? Is incorporating the water cycle, including precipitation infiltrating or flowing over the surface, necessary to elucidate our observations? Regardless of the circumstances, the surface water must have been in a stable, liquid form to erode such valleys, suggesting that the atmosphere during that period was denser than it is currently, at least intermittently. The ambiguous genesis of the primordial rivers on Mars. Ancient valley networks on Mars may resemble analogous landforms on Earth. Nonetheless, distinctions exist. Questions regarding the necessity of invoking terrestrial-type precipitation and floods in Mars's history remain subjects of current dispute. Some river valleys on Mars may have originated from. A specific quantity of branching valleys emerges from the inclines of volcanoes or impact craters, as shown by the Bakuisen crater depicted in the above photograph. One explanation could be that ascending magma elevates the temperature of subsurface water near a volcano, or following an impact, resulting in a convection cell, hydrothermal circulation. Heated water rises to the surface, creating springs and supplying rivers. Lava may accumulate within circular fractures, vaporizing subterranean water and resulting in hot springs and geysers. A lengthy, deeply incised, winding, branching valley exists on the cratered southern plateau. Examples include Nirgal Vallis, Ma'adim Vallis, and Nanedi Vallis. In contrast to the previously delineated networks, these characteristics possess minimal tributaries. Surface water runoff has been proposed as a contributing element. Nevertheless, it does not account for the significant depth, several hundred meters, of the valley's excavation. An alternative explanation suggests that the erosion of the valley flanks, known as sapping, results from subterranean water flows, not surface water movement. The function of precipitation. An increasing number of experts are determining that precipitation, whether rain or snow, has significantly contributed, at least intermittently, to the extensive erosion observed in the planet's most ancient landscapes. In locations where the morphology suggests the presence of ancient subterranean water reservoirs, precipitation was likely essential in the past to replenish those reservoirs. Numerous impact craters exist on Mars, which may have formerly harbored lakes. Approximately 3.8 billion years ago, in an environment conducive to liquid water, the bowl-shaped configurations of craters may have facilitated the development of water bodies and the deposition of sediments, This was merely a theory for an extended period. In 1999, photos from the Mars Global Surveyor revealed unequivocal evidence of such features. The floors of specific craters had highly stratified dark and light strata typically situated in their core areas. On Earth, lakes frequently link to this type of sedimentary deposition. Researchers determined that lakes formerly existed on Mars. The sediments located in Martian craters may have been deposited in lakes supplied by rivers, which would account for the delta-like formations observed in certain deposits near the centers of craters. There are often one or more channels going around the edges of the craters, showing that rivers are active and how water could get into the crater. The dating technique that counts tiny craters verifies that these deposits are ancient, approximately contemporaneous with the river valley networks of the southern high plateau. In other instances, sediments that have been entombed for extended durations have been revealed by erosion, a phenomenon also observed on Earth, albeit to a lesser extent. It's not always evident that the sediments originated from lakes, despite numerous convergent indicators. Occasionally, one might conceive a deposition scenario that is devoid of water. The strata may originate from volcanic activity, resulting in ash deposition. Winds may have transported dust to these areas. The latter hypothesis suggests that the sediments are stratified dunes, with deposition varying cyclically by climate changes. This concept is more plausible than it appears, considering that Mars has endured wind erosion for the past 3 billion years. What formations could the winds have produced over an extended duration? No entity on Earth can provide a comparable experience. Salts and clay inside certain strata offer new insights into Mars's moist history. Liquid water possesses capabilities that extend beyond merely sculpting river channels and moving sediments. The chemical makeup of Martian rocks may have altered, similar to occurrences on Earth. Conducting laboratory mineralogical studies of these rocks would be the optimal method for investigation. Nevertheless, it is now unfeasible. However, we can remotely analyze the composition of Martian minerals by comparing the spectral properties of rocks, such as their coloration, with those of terrestrial samples. In 1998, the TES spectrometer on Mars Global Surveyor identified a unique mineral, crystalline hematite. This is an iron oxide that often necessitates the presence of liquid water for its development. Researchers have identified hematite in ancient sedimentary areas on Mars, such as Terra Meridiani, situated south of Arabia Terra. Is it possible that a lake existed there? An outcrop of sedimentary rocks, seen in false color, is located near the Opportunity landing site in Terra Meridiani. The rock mostly comprises sulfated salts arranged in fine strata, perhaps formed in liquid water. It includes minute mineral spheres, depicted in blue, measuring millimeters in diameter. Some have descended and covered the surface as the wind wears away the rock. To elucidate this inquiry, Terra Meridiani was the location for in-situ investigation by Opportunity, a NASA rover equipped with scientific instruments. Opportunity successfully arrived on January 25, 2004, at a tiny crater measuring 22 meters in diameter. This fortunate opportunity allowed the lander's camera to uncover a light-hued, stratified rock formation on the crater's walls. The Opportunity rover examined these rocks, confirming the presence of hematite. It manifested as millimeter-sized spherical granules termed blueberries, embedded in the bedrock, akin to berries in a muffin. The presence and arrangement of centimeter-scale layers seemingly retained the imprints of waves in shallow water, indicating deposition by liquid water. Opportunity's equipment revealed that the rock primarily consisted of hydrated sulfate salts. On Earth, such deposits develop near the bottoms of shallow lakes, particularly when evaporation intensifies the concentration of dissolved minerals. Geologists perceived that this region of Terra Meridiani had experienced a comparable history. As Opportunity examined the rocks at the Terra Meridiani site, the Mars Express orbiter conducted a comprehensive mapping assessment of Martian mineralogy using its Omega camera. This novel gadget is an astute amalgamation of a spectroscope and an imaging apparatus. It has identified multiple locations with a high concentration of sulfate salts. To the northeast of the location of Opportunity, a massive area spanning hundreds of kilometers has been identified where sulfates are present on specific slopes, constituting the majority of the surface. Many of the sedimentary layers on the floor and walls of Valles Marineris are mostly sulfates, suggesting that liquid water played a part in their formation. Nonetheless, the narrative continues. Omega also identified clays, indicating a distinct era when liquid water traversed another environment. Substantial volumes of water, albeit solely in the remote past, the initial 700 million years of its history, planet Mars likely had multiple distinct phases characterized by varying availability of liquid water. The overall perspective is challenging to reconstruct as time has obscured our clarity, and each event has predominantly obliterated the remnants of its forerunner. On January 4, 2004, the rover Spirit successfully landed on the floor of the expansive Gusev crater. We deployed the rover to this location based on the hypothesis of a lake existing within this crater. Gusev is located at the terminus of Ma'adim Vallis, an extensive valley traversing the elevated southern plateau for 900 kilometers. Based on measurements of the land's surface, Ma'adim Vallis starts at a spillway in the divide of a large drainage basin. Large amounts of water used to flow into Gusev crater, where large sedimentary deposits have been found. Planetologists who harbored significant expectations for Spirit's discoveries were first disheartened. It encountered minimal findings during its 3-kilometer trajectory, primarily consisting of basaltic volcanic rocks over 5 months. Lava flows have obscured all sedimentary deposits from any lake in this region. There were significantly older stratified rocks in the water, historically. The hill appeared to symbolize an island within the lava flow. Hematite was present, along with numerous hydrated minerals such as sulfate salts and goethite, and oxidized iron minerals that require water for their formation. Researchers continued to debate whether this water modification was associated with Ma'adim Vallis. Could it originate from a far more ancient era, of which little evidence persists? The Omega mapping spectrometer on Mars Express identified in particular areas 2 types of Martian rocks indicative of formations resulting from the presence of liquid water: sulfates and clays. We discovered these clays in extremely old landscapes, especially where wind erosion or meteorite impacts had revealed long-buried deposits. During Mars's early history, liquid water could seep into the soil for long enough periods of time for clay to form. Subsequently, sulfated salts were more prone to formation in a drier and more acidic environment. A contentious hypothesis suggests that a body of water originally inhabited Mars' northern hemisphere. Following the tremendous meteoritic bombardment 3.8 billion years ago, the uppermost kilometer of the Martian subsurface likely had a volume of water comparable to a global ocean 500 meters in depth. The observed evidence of ancient rivers and lakes on the southern high plateau indicates that the climate and volcanic and hydrothermal activity may sustain a surface water cycle. Under these conditions, substantial water and sediments must have migrated into lower-lying areas, especially onto the northern plains. Consequently, a vast expanse of liquid water or mud may have existed intermittently in a region referred to as Oceanus Borealis, which would have been 4 times the size of the Arctic Ocean. During that period, Hellas Planitia may have functioned as a genuine inland sea, while the impact basin Argyre might have been linked to the northern plains. Once developed, this ocean would gradually vanish due to evaporation and infiltration into the subsoil. The climate transitioned to a glacial state, sequestering some water in the ground as ice. Certain planetologists hypothesize that oceans may have formed and reformed cyclically throughout the initial few billion years of Mars's early history. Are there any remnants of this ancient ocean? Data from the Molar Laser Altimeter on the Mars Global Surveyor corroborated the concept of a northern ocean. Molar disclosed that elevations remained relatively stable over 1,000 kilometers in areas aligned with historical shorelines. This supports the existence of an ocean, with shorelines creating topographical ledges. This remains an unresolved issue, however. Why did the water not absorb carbon dioxide to form carbonates, such as chalk, if Mars has a carbon dioxide atmosphere? Planetary missions have not identified any such rocks on Mars. Were the oceans, assuming they existed, excessively acidic for such processes? Despite the enduring mystery of Mars's moderate climate, which persists even with a youthful and dimmer sun, planetologists engage in lively debates about the formation of ancient lakes and river valleys. The consensus is that a gradual erosion process by flowing water necessitated rather warm and humid conditions, albeit intermittently. The existence of such a climate is remarkable for two reasons. Mars is relatively distant from the Sun, yet experts indicate that the young Sun was 25% less brilliant than it is currently throughout the relevant period. Under these circumstances, the theoretical average temperature of the world would rise, adding to the enigma of Mars' climate. What were the circumstances on Mars 3.5 to 4 billion years ago? The primordial Martian climate was heated by the greenhouse effect from carbon dioxide and water vapor, together with other less stable gases, and by CO2, ice clouds, that reflected thermal radiation back to the surface. Functioning as a reflective survival blanket, such clouds would have considerably restricted the planet's cooling. Mars's freshly formed and consequently heated interior generated a geothermal heat flux 5 to 10 times more powerful than what is currently observed. This facilitated the heating of the subsurface and the sustenance of a hydrothermal system, which was essential in shaping the Martian climate. Ultimately, the cataclysmic events during Mars' early history may have intermittently resulted in the warming of certain regions. Erosion is gradual, currently, but significantly more severe historically. This image depicts Noachis Terra, one of the oldest regions on Mars, subjected to erosion for around 3.8 billion years. This graphic depicts an expanse measuring 900 kilometers in width. The image indicates the existence of old fluvial valleys, and a meticulous examination shows that most minor craters, under 15 kilometers in diameter, have been obliterated, whilst larger craters have seen significant erosion. Craters in areas with minimally recent surfaces exhibit superior preservation against erosive forces. These data indicate that erosion occurred at some point in the remote past with thousands of times more intensity. A planet is heated by solar radiation and cooled by the emission of infrared radiation into space. The greenhouse effect occurs when cooler atmospheric gases permit sunlight to penetrate them. These gases absorb and retain the infrared thermal radiation emitted by the surface, preventing the planet from cooling. The primordial Martian atmosphere was predominantly made of carbon dioxide, with minor nitrogen, argon, and water vapor constituents. During that period, sufficient CO2 would have existed to sustain an atmospheric pressure of approximately 1 bar, akin to Earth's. Only CO2 and water vapor can contribute to the greenhouse effect in such an atmosphere. Research has shown that these two gases cannot generate temperatures above 0 degrees Celsius. Addressing this issue necessitates the consideration of additional greenhouse gases, including ammonia, methane, and sulfur dioxide. This combination appears improbable, as these gases would have been chemically unstable in a primordial Martian atmosphere unless continuously generated by volcanic activity. Clouds of carbon dioxide ice are probably accountable for the warming of Mars. We can anticipate a dense atmosphere, abundant in CO2, with a propensity to coalesce into clouds of CO2 ice. These clouds might reflect and efficiently retain thermal energy emitted from the surface, thus significantly warming the atmosphere. Refer to the diagram on page 68. We can see a verdant Mars enveloped in thick clouds, beneath which rivers coursed in constant twilight. We require significantly more evidence to substantiate such a scenario. Life emerged on Earth approximately 4 billion years ago. The question that tantalizes the scientific community is, what about Mars? Could life have also taken root on the red planet? What if life on Earth was not the only instance of life's emergence in our solar system? The earliest known sedimentary formations on Earth are around 3.5 billion years old and exhibit indications of life activity. What factors contributed to the early emergence of life on our planet? No one possesses knowledge. We cannot reconcile the disparity between inanimate chemical components and the simplest known life forms. Furthermore, the rocks provide no substantial evidence of such a transition. All theories necessitate the existence of liquid water and concur on the probability that complex organic molecules were delivered to this planet by meteorites and comets, which impacted in significant quantities during that period. Volcanism and hydrothermal activity have significantly contributed by supplying energy and nutrients. Similar conditions existed on Mars as well. If life on Earth originated from fundamental and recurrent physico-chemical processes, there is no a priori justification for excluding the possibility of life emerging on Mars 3.5 to 4 billion years ago. Research on Mars indicates that surface conditions permitted liquid water for a finite duration, at most, several hundred million years. Any life form that may have emerged there would have been exclusively primitive. Multicellular species, including the initial animals and plants, emerged on Earth after over 2 billion years of unicellular progenitors. Was this due to the extensive period required for essential genetic evolution? Or was it a result of Earth's physical and chemical circumstances, such as oxygen levels being unsuitable for the presence of more sophisticated organisms? It is possible that events on Mars transpired differently, and certain hopeful scientists have conjectured that more advanced life forms may have coexisted there concurrently. Mars, being smaller than Earth, likely cooled at a significantly faster rate. Furthermore, it did not undergo the significant impact that resulted in the birth of our moon, and likely deprived the Earth of its primordial atmosphere, some 4.5 billion years ago. Life may have originated on Mars before its emergence on Earth. During its formative period, Mars endured several meteoritic collisions. These frequently expelled pieces of the planet's surface into space. Many have impacted Earth, and may continue to do so. Within these fragments, circumstances may permit the survival of diverse spores. A compelling idea posits that Martian species may have traversed interplanetary space and seeded Earth 4 billion years ago. What methods might we employ to investigate remnants of life that vanished billions of years ago? This question is not just a scientific curiosity, but a crucial quest that could potentially reshape our understanding of the universe and our place in it. The revelation that life previously existed on Mars would be one of the most significant scientific and philosophical milestones in human history. Simply illustrating its absence would be intriguing as we ponder the question: why did life arise on one planet and not the other, despite both displaying similar conditions? Mars offers a superior research environment to Earth, where evidence of events from over 3 billion years ago has been obliterated. A potential clue to the missing link between inanimate and biological matter may be found on the red planet. What criteria should we consider? Typically, post-mortem, living cells undergo fast decomposition, resulting in the complete loss of their shape. Nonetheless, mineral fossilization has frequently enabled the reconstruction of numerous ancient microorganisms, shapes, appearances, and organization. This process includes silicates in aqueous solution, progressively depositing onto organic molecules within cells, creating a solid mineral matrix that can preserve intricate characteristics, such as the roughness of a bacterial membrane. A similar procedure may have transpired on Mars as well. If any living form ever developed there, we may eventually discover hints of its morphology. Where shall we commence the search? Numerous scientists pose this inquiry as missions designed to return samples to Earth are being developed. Sedimentary basins, where water may have been collected, are preferred locations. Holden Crater, A, B, is 1,000 kilometers north of the Argyre Basin. Ancient lake locations are particularly intriguing, as it is conceivable that any Martian life present may have persisted in a stable habitat after the average temperature of the site declined below 0 degrees Celsius due to a substantial layer of permanent ice. Such locations are seen in the Antarctic dry valleys, CC. They have been the subject of numerous investigations by NASA experts. Notwithstanding the lack of precipitation and sub-zero temperatures, except a few days annually, these Antarctic lakes harbor an unexpected abundance of ecological niches. D. Bacterial colonies, spanning several tens of centimeters, blanket their depths. A further line of inquiry involves the pursuit of biological matter remnants. Regrettably, the Viking landers revealed that Martian soil is chemically highly aggressive, containing oxidizing chemicals that likely obliterated all organic molecules within the uppermost few meters of its surface. Identifying the mineral or biological origin of such compounds, discovered at greater depths, presents a problem. Current experiments on Earth indicate that most complex chemicals associated with live organisms should have completely vanished on Mars after 3.5 billion years. Nonetheless, there exists the potential for the continuously frozen soil to preserve certain exceptionally resilient chemicals. Any life that previously existed on Mars may have concentrated specific chemical components at proportions that are challenging to account for through non-biological processes. Pyrite, magnetite, and phosphates are present in significant concentrations within living cells on Earth. The biological activity employs them as markers. All living organisms on Earth preferentially utilize carbon-12 over carbon-13, a chemically similar yet heavier isotope. Mars, like Earth, might likewise perceive this event. Most SNC meteorites from Mars are relatively recent basaltic rocks, with dates ranging from 180 million to 1,400 million years. Only one specimen differs, ALH 84001, discovered in the Allen Hills, thus the acronym, in Antarctica in 1984. This rock originated about 4 billion years ago in a temperate and chemically reducing environment, markedly distinct from the oxidizing conditions present on Mars today. ALH 84001 exhibits fissures indicative of water movement approximately 3.6 billion years ago, resulting in the deposition of prominent carbonate nodules. These measure around 1/10 of a millimeter in diameter. This meteorite contains organic compounds. It is a valuable and singular testament to Mars's era as an oasis. Following its detection in 1993, this remarkable meteorite garnered global notice. In 1996, a group of American researchers led by David McKay of NASA garnered international attention by proposing that ALH 84001 could harbor evidence of extraterrestrial microbial life. However, where was the evidence? This is the extraordinary narrative of a meteorite that originated from Mars. The chronology of this meteorite has been reconstructed utilizing isotopic dating techniques on the elements embedded in the rock through crystallization, 4.5 billion years for volcanic rock, and 3.6 billion years for carbonates. Thermal events post-impact, 4 billion years, and the rock's exposure to cosmic rays during its traversal through space. Analysis reveals that cosmic rays initiated the formation of new isotopes 16 million years ago, with the process terminating abruptly 13,000 years ago. An analysis of meteorite ALH 84001 was undertaken. Upon detection, the object was covered by a fusion crust, characteristic of meteorites heated by friction during its transit through the Earth's atmosphere. B. When bisected, ALH 84001 exhibited many fractures and cavities. The microscope showed unusual spherical carbonate inclusions measuring 100 and 200 micrometers, 0.1–0.2 millimeter in diameter. These entities comprise less than 0.5% of the total. D. Scanning, electron microscope view of a carbonate surface. Little stick-like structures formed by a series of purported fossils measuring less than. Initially, complex organic molecules known as polycyclic aromatic hydrocarbons, PAHs, were present, potentially resulting from microbial breakdown. Secondly, the morphology and chemical composition of the carbonate nodules resembled deposits formed by specific terrestrial bacteria, notably exhibiting abundant layers of iron oxides, including magnetite. Finally, fossils, measuring less than 1 millimeter and resembling microorganisms, were observable under the electron microscope. Over the years, numerous scientists challenged the validity of Mackay's findings. Could the microfossils result from abrasion and surface modification during observation? Could the PAHs, carbonate nodules, and magnetite deposits be attributed to natural mineral processes? Ultimately, while it was established that the carbonate deposits were ancient and of alien origin, it was deemed likely that some of the organic materials originated from contamination of the meteorite during its 13,000-year residence under the Antarctic ice. Although ALH 84001 may not constitute definitive evidence of past life on Mars, it substantiates that during its formative years the planet provided temperate and likely humid circumstances, whereby organic compounds would not have been rapidly obliterated by oxidation. What factors prevented Mars from following a trajectory similar to that of Earth? Mars formerly exhibited a temperate and moist, Earth-like climate. The planet is currently frigid and arid, with a sparse atmosphere that precludes the existence of rivers. A consensus among scholars indicates that Mars reached a pivotal moment in its fate, when it lost most of its atmosphere. What circumstances led to this occurrence? During the initial billion years of their existence, Mars and Earth experienced collisions with asteroids several kilometers in diameter, and these powerful impacts may have expelled a significant portion of Mars's primordial atmosphere into space. The Earth's superior gravitational force enabled it to retain its gases more effectively. The loss by impact explanation fails to elucidate the reasons behind Mars's current low atmosphere. According to calculations of atmospheric erosion, the Martian atmosphere was significantly denser following the period of heavy bombardment. In liquid water, atmospheric carbon dioxide chemically combines with surface rocks to produce carbonates, diminishing the air volume. Tectonic processes on Earth perpetually recycle rocks, maintaining equilibrium in this process. Volcanoes then release carbon dioxide into the atmosphere after submerging carbonates into the Earth's interior. On Mars, where plate tectonics is non-existent, most of the atmosphere would have been converted into carbonates at the surface. The inquiry then emerges. Where are these carbonates located? No conclusive evidence of their presence has been discovered, even by the Omega mapping spectrometer on Mars Express, which can detect minimal quantities. The ALH 84001 Martian meteorite revealed few traces. Has the Martian environment obliterated all remnants of carbonates on the planet's surface? One can conceive of a scenario in which carbonates did not arise. If Mars's primordial environment facilitated sulfate deposition, surface water would have been comparatively acidic, precluding the formation of most carbonate types. A planet must possess adequate gravity to maintain its atmosphere. For instance, on a comparatively diminutive body like the Moon, the mere thermal motion of a gas molecule suffices to facilitate its escape into space. Nonetheless, this loss is insignificant on Earth, save for the lightest gases, hydrogen and helium. What is the current status of Mars? The red planet possesses sufficient mass to retain substantial amounts of carbon dioxide and water vapor. However, more processes result in the ejection of atoms and molecules. Reactions caused by solar UV radiation and the interaction of the solar wind with high-altitude ions are contributing causes. The Earth's magnetic field deflects the solar wind beyond the atmospheric boundary. Mars has lacked a magnetic field for millennia, allowing oxygen ions to be significantly accelerated in its upper atmosphere by the solar wind's magnetic field, colliding with CO2 molecules and expelling them into space. Can hidden carbonates on Mars be discovered? It is theorized that a portion of the old Martian atmosphere may have been sequestered in the Martian subsurface as carbonates. The surface lacks these carbonates. Nevertheless, several instances of ancient rivers, e.g. Hebrus valleys, appear to have sculpted their beds both at the surface and subsurface by dissolving rocks to create a karstic hollow. This morphology is characteristic of Earth's limestone regions, which are abundant in carbonates. Is the subsurface material in this area comprised of a layer of carbonates currently obscured by dust? Is it possible for early life forms to have endured in such a hazardous environment? The Viking probes undertook an exploration for life on the surface of Mars. One of the primary aims of the Viking probes was to identify life on the Martian surface in 1976. An articulated arm designed for excavation collects samples of Martian soil. We examined the samples. Pyrolytic release, gas exchange, and labeled release trials. Mars is currently frigid and arid. Without a protective ozone layer, its surface is subjected to extreme UV radiation, which would be fatal for most living species, particularly those similar to those on Earth. The upper layers of soil appear to have been sterilized by highly oxidizing substances in the environment, akin to the oxygenated water utilized for microbial eradication. Under these circumstances, if life began on Mars, how could it have persisted to the present day? Even the most hopeful experts exercise caution regarding this topic. It is important to note that the exploration of our planet has demonstrated that certain microbes can endure the most harsh circumstances. They continue to thrive despite enduring extreme pressures, temperatures exceeding 100 degrees C, very acidic or alkaline environments, or relying on hydrogen sulfide or iron for sustenance. In 1995, researchers identified creatures with an iron-based metabolism residing in basaltic rock in Oregon, many kilometers beneath the Earth's surface. It appears that liquid water is essential for the survival of all life forms. If life has persisted on Mars, we must search for it in crevices where liquid water remains. A potential location is many kilometers beneath the surface, where the planet's geothermal heat maintains temperatures above 0 degrees C. Interstitial water may support life, similar to the Oregon instance. Proximal to the surface, Martian volcanism, although diminishing, likely generates warmer areas. Like Earth, life may utilize such locales, more abundant chemical resources. One might conceive of liquid water bodies developing beneath the permanent polar caps of Mars, akin to subglacial Lake Vostok in Antarctica. The Viking probes performed an investigation of Martian soil. The pyrolytic release experiment was devised to explore the potential for Martian organisms to assimilate carbon dioxide, akin to the technique employed by specific terrestrial species, photosynthesis. No such activity was identified. The gas exchange experiment aimed to identify gases generated by microorganisms that have metabolized organic materials. A significant amount of oxygen was identified. However, as it continued to be created after the sample was sterilized by heating to 145 degrees C, it was determined that the oxygen originated from the chemical oxidation of the substance. The experiment revealed that the Martian surface is an oxidizing and sterilizing environment, akin to a medical disinfectant, rather than indicating the presence of life. We devised the label release experiment to identify the conversion of organic matter into carbon dioxide via radioactive labeling. The outcome was affirmative. A change occurred, which halted immediately upon heating the sample, precisely what would be anticipated in the presence of bacteria. Ultimately, the ruling was unfavorable, since alternative equipment, a gas chromatograph paired with a mass spectrometer, which can detect organic compounds at concentrations below 1 part per billion, revealed no findings, astonishing all parties involved. Most experts, albeit not unanimously, believed that the labeled release experiment demonstrated the functioning of inorganic processes in an oxidizing environment, as indicated by prior experiments. UV radiation and oxidation have entirely eradicated all natural organic stuff from the surface of Mars. For life to have persisted on the red planet, Martian creatures would have required a stable environment inside their bio-niches. Considering a planetary evolution spanning billions of years, this appears unlikely. Yet, what unexpected revelations would future discoveries unveil? A temporal exploration of Mars over billions of years reveals that, as millennia elapsed, lava, ice, and intermittently flowing water collaborated to sculpt the planet's surface, resulting in the Mars we observe today. Only limited insights into that history are accessible to us, refined by geologists in light of recent discoveries. Every space mission invariably presents us with unexpected revelations and difficult inquiries. Mars's thermal energy dissipation is the impetus for all geophysical phenomena. In its early stages, Mars exhibited its vigor. Its colossal volcanoes indicate that the planet was once sufficiently heated to facilitate extensive volcanism. Its primordial and current atmosphere and water may have originated from the mantle as volcanic gases. Nevertheless, this intense eruptive phase quickly resulted in a process via which interior heat was progressively dissipated via convection. This document outlines the history of Mars's mantle and its magnetic field. Between 4.4 and 4.0 billion years ago, vigorous convection currents transpired in Mars's mantle, refer to diagram, mantle epoch Y, resulting in surface renewal, a notion that remains unverified. The loss of heat by convection from the mantle induced convection within the iron core, resulting in movements that generated a magnetic field, core epoch A. After several 100 million years, convection diminished, and the crust stabilized at the surface. The planet entered its single-plate tectonic phase, epoch LA. The convection diminished in intensity, leaving only a few hot spots, epoch LLB. In the core, convection transitioned to conduction as the mechanism of heat dissipation, resulting in cooling. The movement within the core and the resultant magnetic field ceased, epoch B. Cooling will persist, and convection will cease in the mantle, epoch All, solidifying a portion of the core, epoch C. Mars will subsequently remain tectonically inactive. The genesis of convection. The internal heat of Mars initially originated from accretion and the subsequent creation of an iron core, subsequently sustained by the radioactivity of uranium, thorium, and potassium in the mantle. In the frigid expanse of space, a planet will undergo cooling once all its energy from formation and radiation is dissipated as heat. Convective currents in the mantle transport internal heat from the core to the surface. Similar to the movement of water when heated in a saucepan, the solid Martian mantle deforms and shifts, gradually bringing warmer material from the depths into contact with the cooler layer near the surface. although in actuality convection is restricted to the region between the core and several hundred kilometers beneath the surface. Convection in the mantle cools the core's surface, instigating additional core convection. This creates the chain of cooling that will define the planet's surface throughout its lifetime. The progression of convection. Mantle convection occurred vigorously during the initial 2 billion years of Mars history. Disintegration or ascent into the crust in lavas progressively eliminated the most radioactive elements from the mantle. However, convection did not completely terminate. As indicated by certain theoretical models, the gradual decline of convection on Mars is attributed to the crust, now infused with radioactive materials, functioning as a thermal insulator over the mantle. The continental crust accounts for 30 to 40% of Earth's heat production. The increasingly dense carapace of Mars has encased its mantle within a stiff and insulating layer referred to as the lithosphere. The depth ranges from 500 kilometers south to 150-250 kilometers in the north. Mars has replicated the Moon, which possesses a lithosphere 800 kilometers thick and retains its liquid core. The red planet likely possesses a heated mantle and a molten core, with some scientists suggesting that the mantle may be partially molten beneath some volcanoes due to the insulating effect of the crust, where recent lava flows have been detected by Mars Express. Volcanoes compete to be the largest. Mars's prominent features include its colossal volcanoes. They are numerous and diverse, with some colossal. They report on recent geological activity. The Tharsis and Elysium regions host the planet's most formidable volcanoes. Historically, they emitted significant gases including CO2, SO2, and water vapor, likely resulting in climate warming and sulfate deposition. The Tharsis region features a substantially elevated bulge, measuring 5,000 kilometers in diameter and 5 kilometers in height, situated atop colossal extinct volcanoes. Arsia Mons, Pavonis Mons, Ascryos Mons, and Olympus Mons. All these formations exhibit morphological similarities to their terrestrial counterparts, the shield volcanoes of the Hawaiian Islands. Their inclines are gentle, not surpassing 6 degrees, and they have collapsed areas, calderas, at their peaks. These formations result from accumulating highly fluid lava flows, emphasizing their gradual inclines and broad bases. The Paterae. These pie-shaped volcanic formations may span hundreds of kilometers in width. They predate the shield volcanoes of Tharsis. They are located near Tharsis, e.g. Apollinaris Patera, and within Elysium, Hadriaca Patera, Terina Patera, and Amphitrite Patera. Their structure includes a central caldera and lava flow canals along the flanks. Alba Patera, north of Tharsis, and Apollinaris Patera have had explosive hydrothermal events driven by interactions between their magma chambers and subterranean water. The resultant explosions were marked by the expulsion of pyroclastic material and dense ash clouds referred to as nuées ardentes. It is believed that these ash deposits, known as ignimbrites, were subsequently eroded, resulting in troughs extending several kilometers that were carved into them around the caldera. A phase of effusive, fluid lava activity would have followed the explosive occurrences. These volcanoes represent a distinct category. They predominantly inhabit the Tharsis region, adjacent to the shield volcanoes. They are inferior in size to the latter. Their pronounced inclines, about 8D, may be attributed to a more viscous type of lava. It is plausible that some displayed a subsequent explosive phase. Olympus Mons is a giant. Its volume is 50 to 100 times bigger than the greatest terrestrial volcanoes. What is the process of its formation? It is just an aggregation of lava flows from a subterranean magma reservoir. On Earth, this type of volcano is called Hawaiian, named after those found in the Hawaiian Islands, which rise over 7,000 meters above the ocean floor. The magma chamber of the colossal Olympus is at least 3 times larger than that of a Hawaiian volcano. Nonetheless, the explanation for its immense size lies not in its formation, but in the duration of its development. Plate tectonic processes on Earth displace the crust above the magma chamber as lava flows, resulting in smaller volcanoes, such as those found in the Hawaiian Islands, rather than a single huge volcano. Due to the absence of tectonic activity on Mars, successive layers of lava have emanated from the magma chamber of Olympus Mons, accumulating over hundreds of millions of years. Olympus Mons may resemble a Hawaiian volcano due to its 6-degree slopes, although it also exhibits traits typical of Icelandic volcanoes. For instance, an escarpment 6,000 meters in height surrounds its base. The volcano's substantial mass probably formed this structure by distorting the strata of lava and ash. The caldera of Olympus Mons measures 80 kilometers in diameter and has a depth of 2,600 meters. It comprises 6 overlapping calderas. The substantial mass of the volcanic dome induces slumping, resulting in visible fissures. Refer to the photograph on page 95. Extensive aureoles extend up to 700 kilometers to the northwest of Olympus Mons. The origin of these aureoles remains unclear. The erosion of volcanic deposits or significant fracturing could generate them. Alternative explanations cite the presence of prehistoric glaciers. The HRSC camera on the European Mars Express spacecraft has significantly enhanced predictions regarding the timing of the most recent volcanic activity on Olympus Mons. Crater counts suggest that the peak caldera was produced between 100 million and 200 million years ago. The last lava flows on the volcano's slopes are around 2 million years old. Olympus Mons may still be active. Lava has sculpted vast regions of Mars. Mars's volcanism can produce formidable formations such as Olympus Mons. Lava's viscosity varies, resulting in numerous other properties. Evidence of multiple lava flows, some quite recent, extends hundreds of kilometers from the flanks of most Martian volcanoes, including Tharsis, Elysium, Hellas Planitia, and Syrtis Major. These flows resembled those of Hawaii's shield volcanoes, but their volume may have been 5 times greater. The lack of plate tectonic activity on Mars and its diminished gravity and low atmospheric pressure resulted in the expulsion of significantly larger quantities of gas, lava, and ash. Extensive lava sheets, with their obscure origins, are distributed throughout plains like Utopia, Acidalia, and Lunae Planum. Fractures and faults are believed to facilitate the ascent of this notably flowing lava. This kind of volcanism closely mimics that of the lunar Maria, with the primary distinction being that volcanic activity on the Moon halted 3 billion years ago, whereas on Mars, lava flowed very recently. Natural exposures along the slopes demonstrate that successive deposits have amassed to a depth of several kilometers. Since the conclusion of the meteoritic bombardment 3.8 billion years ago, over 60 million cubic kilometers of lava have been dispersed throughout the Martian plains, averaging 0.016 km 3 annually. The cumulative volume of the volcanic deposits, including volcanoes and basalt plains, is around 500 million cubic kilometers. Until quite recently, Mars exhibited geological activity. The colossal volcanoes of Tharsis attest to this fact. Intense convection currents in the mantle and their interactions with the crust have resulted in volcanism and significant surface alteration. Certain surface deformations manifest as extensions or expansions of the crust, whilst others exhibit compressive characteristics. Tharsis is notably intriguing. Convergent convection currents beneath have elevated and thickened the crust in this area. The ascendant movement induced stretching, resulting in a radial array of faults emanating from the epicenter of the uplift. Collapsed troughs, graben, frequently occur between the faults. Certain compressive structures manifest as ridges organized concentrically around the bulge's core. The ridges on Lunae Planum resemble those found on the Luna Maria. These linear landforms extend for hundreds of kilometers. Their mean width is 5 kilometers, and their maximum elevation is approximately 300 meters. They are likely a consequence of surface compression. The crust secures these compressive or wrinkled ridges to depths of many kilometers. At these depths, the existence of volatile substances, including water and hydrous or carbonic ice, has undoubtedly facilitated the sliding of one layer over another. These ridges may indicate the contraction of the Martian crust during the planet's cooling period. One of Mars's most remarkable features is its extreme topography. Mars possesses the largest canyon in the solar system, Valles Marineris. The canyon measures 3,500 kilometers in length, 300 kilometers in width, and 7,000 meters in depth. Valles Marineris extends eastward from the Tharsis volcanoes nearly parallel to the equator, formed as Tharsis ascended due to the expansion of Mars's crust. This extension established a network of parallel faults within a convoluted configuration of collapsed trenches. Certain planetologists perceive the Valles Marineris complex as a significantly larger analogue of the East African Rift Valley. On Mars, the plateau has subsided and descended to 7,000 meters. The crust stretching permitted magma to ascend into the faults, which receded, resulting in localized surface collapse. This occurrence has resulted in depressions resembling lines of adjacent craters along collapsed trenches. Landslides have expanded the chasms of Valles Marineris. In the center region, which reaches a depth of 5,000 meters, the canyon expands to create extensive, elongated depressions referred to as chasmata. These features possess steep inclines and occasionally exhibit floor deposits that have collapsed and dispersed over lengths as great as 200 kilometers. The dimensions of these fans have prompted experts to estimate that the landslides from whence they originated down at velocities around 300 km/h. The canyon floors exhibit substantial stratified deposits in several areas. These antique features possess an enigmatic origin. The Omega mapping spectrometer on Mars Express indicated that certain areas are abundant in sulfates, perhaps produced via the evaporation of shallow lakes, or from precipitation involving highly saline water. Craters in permafrost are frequently observed. Lobate ejecta deposits surrounding the impact crater, left, are likely attributable to subsurface material abundant in ice. The crater's diameter measures 10 kilometers. The diagram illustrates the instant of impact, during which a rapid temperature increase induces ice melting, resulting in ejecta comprised of substantial amounts of water, ice, and water vapor, forming a type of nume ardente. Subsequently, after retreating, the ejecta traverse the surface for a considerable distance, resulting in the formation of the visible lobes. Lobate ejecta craters indicate the properties and condition of the subsurface material during impact events. Meticulous examinations of their morphology can yield insights into the depth and ice composition of the permafrost. Mars's average annual surface temperature is 70 degrees, well below the freezing point of water. Nonetheless, stable ice formations exist solely in the polar areas of the Earth. In tropical latitudes, frost occasionally occurs before sunrise, swiftly sublimating as temperatures increase during the morning. As the sun heats the surface, the lowest atmospheric layer becomes sufficiently desiccated, causing ice to sublimate even at sub-zero temperatures. During winter, in mid-latitude regions or on shaded inclines, ice may persist for weeks. Nevertheless, it will become unstable at the surface when spring warming commences. Nevertheless, if the ice is relatively insulated from the atmosphere, for instance beneath a layer of dust, and temperatures remain sufficiently low, it may be stably preserved in the solid state. Water may exist on Mars above latitude 40 degrees as ice in subsurface holes. In regions on Earth, such as northern Siberia or Canada, Conditions akin to those described result in subsurface material being frozen to depths of several hundred meters, known as permafrost. Is it possible for Mars to possess ice-rich permafrost? A multitude of observations corroborate this. Although most impact craters in the solar system are encircled by radially ejected material, several Martian craters exhibit ejecta with a lobate morphology akin to mud flows. These craters offer scientists significant evidence of ice-rich permafrost beneath the Martian surface. Lobate ejecta craters observed by the Themis camera on Mars Odyssey in 2002. The image on the left depicts a human visible crater in the Chrysoplanitia region, recorded in visible light. Conversely, the right image features nighttime photographs of craters in the Alcides Planitia region, obtained by the camera's thermal imaging technology. Temperature disparities associated with changes in the ejecta material's composition and texture elucidate each crater's distinctive characteristics. The vast ejecta surrounding this type of crater on the northern hemisphere plains indicates the existence of significant quantities of water ice at the time of impact. Even the minutest craters exhibit lobate ejecta, indicating a subsurface soil abundant in ice. This abundance in the northern plains likely indicates an uneven ice distribution in the Martian subsurface. Outflow channels and the theoretical oceans have undoubtedly facilitated the formation of extensive ice-rich permafrost over the northern hemisphere. Mars possesses subsurface water. Above the permeable and ice-laden permafrost, many more contemporary icy deposits have been recognized. The ice has predominantly been conveyed through the atmosphere, deposited and then insulated and safeguarded by a layer of sediments, except in polar regions where the ice remains exposed. Global permafrost commences at an estimated depth of 300 meters to 1 kilometer in the equatorial region, and between 300 meters and under 10 meters in mid and high latitudes, where typical temperatures below 70 degrees C facilitate permafrost stabilization near the surface. The permafrost depth is estimated to range from 1 to 3 kilometers in the equatorial zone and from 3 to 7 kilometers in higher latitudes. At these depths, the pressure from geological strata and geothermal heating from the planet's interior typically result in liquid water. The eastern terminus of the Valles Marineris canyon system on Mars's equator transitions suddenly into an extensive topographical depression, with a surface area surpassing that of France. In this region, disordered, chaotic landscapes penetrate the cratered plateau to depths approaching 3 kilometers. Some of these are vast enclosed depressions extending several hundred kilometers. They possess an enigmatic origin. Extensive, profound outflow valleys are intricately linked to these landscapes. The Hydaspes Chaos region, located at the Valles Marineris terminus, is a commendable illustration. The tumultuous landscapes feature prominent pyramidal buttes of approximately 1 kilometer height, aligned along orthogonal faults and evenly distributed. What is the process by which such terrains are formed? One of the primary enigmas is the lack of any exit or fissure via which the originally existent material may have been expelled. According to a commonly accepted view, permafrost initially encompassed this area of the cratered plateau. The warming of subsurface material from volcanic activity or climatic changes led to permafrost melting, resulting in terrain collapse in certain areas. Another inquiry persists. Where was all the solid material, sediments and rocky debris transported during this thaw? One explanation could be that in this region's permafrost, ice was particularly prevalent, while rocky material was limited. The volume would have markedly diminished when the ice melted, and the land subsided. The concept of ice-rich permafrost is accurate. The aggregate volume of water excavated from these rugged terrains would suffice to envelop the entire world to a depth of 40 meters. Extensive canyons sculpted by catastrophic floods. To the northeast of Valles Marineris, vast, profound valleys traverse the cratered plateau, and reached towards the expanse of Chrysoplanitia. Upon their discovery, significant excitement ensued, since it appeared probable that they had been shaped by the action of rushing water or mud. Nonetheless, their origins and form have few similarities with those of the river-valley networks on the cratered plateau. Several of these features are relatively recent in geological terms. The outflow channels exhibit a distinctive morphology. They lack tributaries and have a limited geographical origin. Numerous channels traverse the floors of these formations, navigating past significant impediments like impact craters, creating teardrop-shaped structures that taper in the flow's direction. The configuration of these streamlined islands has prompted researchers to determine that they were sculpted by very turbulent flowing water, rather than by ice, lava, or sediment. Geomorphologists assert that only abrupt, ephemeral surges of substantial water volumes may elucidate the features of the outflow pathways. One can estimate the volume of water involved in these catastrophic events by analyzing the widths of the channels. Consider Ares Vallis, which spans 25 kilometers in width. If we hypothesize a water layer of 10 meters in depth, the highest discharge rate may have exceeded 100,000 cubic meters per second. Alternative outflow pathways on Mars may have undergone discharges of over 70 million cubic meters per second, exceeding 2,000 times the volume of the Mississippi River. What is the source of this water? We have proposed multiple scenarios. Mike Carr of the U.S. Geological Survey, California, posits that the floods in the outflow canals north of Valles Marineris result from pressurized subterranean water storage in Mars's permafrost abruptly releasing its contents. This reservoir could provide around 10 trillion cubic meters of water. In certain channels, such as Athabasca Vallis, the water originates from the thawing of permafrost, induced by lava ascending through crustal fissures. What is the appearance of outflow channels from an internal perspective? In July 1997, the Pathfinder lander and the small robot rover Sojourner sent a panorama of the Ares Vallis outflow channel. Disordered rocks, measuring several millimeters in diameter, were scattered across the meager dunes. In 1976, Viking 1 captured images of the identical terrain around 800 kilometers to the northwest. This is the location of the Pathfinder landing. This extensive photograph, left, from the Viking orbiter 1976, depicts the Pathfinder landing location on a broad, flat plain devoid of significant topographical features. Evidence of water's flow is apparent. A butte near the source of a streamlined landform appears to have been situated in the center of a flood. What is the origin of the rocks? Did the massive torrents of water or dirt that traversed the rivers in the past convey them here? Did they depict ejecta from nearby impact craters? Could they be the vestiges of the indigenous local rocks, eroded over time? All three hypotheses are viable. Certain blocks exhibit a triangular shape and are characterized by striations, indicating the influence of significant wind erosion. See pages 134–136. Others exhibit pronounced rectilinear ridges, indicating they are likely ejecta from intense meteoritic strikes. Numerous blocks in the image intersect or are positioned at angles, suggesting that a flowing liquid may have deposited them. What is the reason for the orange coloration of the ground? The planet's surface selectively reflects red light while absorbing violet and blue light. Numerous languages reflect the planet's color in their nomenclature. In ancient Egypt, Mars was interpreted as the Red One. In India, Lohitanga was referred to as red-bodied. And to the Romans, Mars, the god of war, was linked to blood. Analytical chemistry. Spectrometer analyses conducted on Sojourner indicate that most of these blocks consist of andesite, a volcanic rock generated in the past, blue arrows. A thin layer of dust, a few micrometers thick and abundant in magnetized iron oxides, magnetites, red arrow, envelops all these blocks. The soil possesses a thin layer abundant in magnesium sulfate. This composition indicates the existence of mineral salts, perhaps deposited following the evaporation of water in the past. Scientists have historically regarded Mars as a rusty planet due to its coloration, and data from Pathfinder indicated that the soil contains approximately 17 to 18% ferric oxide, Fe2O3. Ferric oxide is Martian soil's second most prevalent component, following silica, silicon dioxide, SiO2, at around 43%. 2 decades prior, Vikings 1 and 2 recorded nearly identical soil compositions at their respective locations, indicating that the Martian surface is enveloped by a fine layer of uniformly distributed dust, altered by dust storms over billions of years. What accounts for the abundance of iron on Mars? Analysis of the SNC meteorites from Mars indicates that, on average, its mantle contains 2.5 times more iron than the Earth's. The likelihood is that Mars's diminished gravity has rendered the differentiation process less effective. Scientific motivation derived from the east. The valley contains the River Lena and the Martian discharge channels. The Lena River, left, extending 4,000 kilometers, features a floodplain 25 kilometers wide downstream of Yakutsk, the capital of the Yakutia Republic in Siberia. Source: NASA, Landsat. The riverbed exhibits numerous characteristics akin to the outflow canals found on Mars. Both have formed above permafrost and are of equivalent scale, including minor longitudinal gradients and minimal tributaries. Episodes of violent flow during the Siberian spring indicate potential occurrences on Mars. We designate these floods as catastrophic because of their substantial water volume. The Lena River's flow reaches 50,000 cubic meters per second, while the flooding in Ares Vallis is estimated to have been as high as 100,000 cubic meters per second. The confluence of the Martian Valley Simud and Shalbatana, right, is marked by numerous waterways. Channels bifurcate in specific valleys, such as Simud, creating elongated islands. These characteristics closely resemble those seen in the Siberian flow valleys of central Yakutia. Significant fluctuations in flow across seasons or months generate numerous channels, resulting in extensive valleys characterized by flat, shallow channels. The planet Mars exhibits similarities to Siberia in certain aspects. Temperatures on Mars can plummet to 100 degrees C during the equatorial winter and ascend to +23 degrees C in the summer. In central Siberia, winter temperatures can reach 70 twandings, while summer temperatures may rise to +30°. In these harsh conditions, low temperatures contribute to the formation of extensive and persistent permafrost, which is crucial to the landscape's evolution. It creates a true carapace, described as stiff as concrete. In central Yakutia, the Siberian Sakha Republic, the permafrost depth can reach 1,500 meters. We may discover analogous values on Mars. Accelerated erosion transpires in frozen banks. During spring in Siberia, the thawing of the river and the melting of snow converge to produce a significant outflow capable of eroding riverbanks by 30 meters within a few months. This erosion reveals substantial ice layers within the permafrost, shown by arrows. This 25-meter cliff is located on the Lena River. Planetologists assert that analogous layers are present in Mars's northern hemisphere plains. Researchers examine permafrost in a laboratory setting. Planetologists endeavor to replicate the specific conditions under which certain processes transpired on Mars and in Siberia within a laboratory setting. The image depicts a hydraulic channel established in a cold chamber by researchers at the University of Orsay to investigate thermal erosion processes in frozen soil, akin to flow events on Mars. Examine the existing Martian weather, characterized by storms, dust devils, snowfall, trade winds, and anticyclones. Daily atmospheric dynamics sculpt the Martian terrain, which meteorological variations affect. The red planet's temperature is not static. It has experienced gradual and significant swings throughout millennia due to orbital variations. Spring arrives on Mars's northern hemisphere. In the northern winter, a layer of carbon dioxide snow continues to envelop the North Pole. In the southern mid-latitudes, depressions generate intense winds that elevate fine mineral dust. Dust storms occur beneath the pale rings of ice crystal fog, a hypercontinental climate. Currently, Mars is characterized by transformation. Its seasons and climatic variations drive these changes. Since the 18th century, astronomers have observed the reduction of Martian polar caps during spring, altered cloud patterns, and even surface color variations. These occurrences did not surprise observers. They reinforced the belief that Earth is the archetype for all planets. Moreover, observers noted that Mars rotates on its axis for a duration comparable to an Earth day, 24 hours and 40 minutes. Additionally, both planets possess similar obliquity angles in their equatorial planes relative to their orbital planes, 25.2 degrees for Mars and 23.4 degrees for Earth. Mars exhibits 4 seasons like Earth, although one Martian year encompasses 669 Martian days, equivalent to 687 Earth days. However, for ancient astronomers, these similarities did not render Mars another Earth. The duration of a year on Mars is referred to as the Martian year. While Mars experiences a seasonal cycle similar to Earth, its orbit is more eccentric, resulting in a longer year. At perihelion, the point in Mars's orbit closest to the Sun, which occurs annually after southern spring, the planet is approximately 20% nearer to the Sun than during the opposite season. Consequently, Mars receives nearly 50% more solar energy. The planet's velocity is maximized at perihelion, leading to significant disparities in the length of its seasons. The southern summer is characterized as warm yet brief. The map depicts surface temperatures of Mars's southern hemisphere, generated from data obtained by the Themis infrared camera, a component of the Mars Odyssey mission. The temperature differential between day, red, and night, blue, is apparent. At the South Pole, a carbon dioxide snowcap, recorded at 125 degrees, remains visible from the preceding winter. During a pleasant afternoon on Mars in the southern summer, temperatures may reach a mild 20 degrees, accompanied by a gentle trade wind. However, nighttime brings frigid conditions, with temperatures plummeting by several degrees to 100 degrees and persisting until dawn. Refer to the temperature chart on page 124. Martian soil is arid, granular, and ineffective at retaining heat, exhibiting significantly low thermal inertia compared to Earth's surface, particularly its oceans. Additionally, Mars's tenuous atmosphere makes temperature fluctuations considerably more pronounced. In summary, Mars's climate is characterized as hypercontinental. The seasonal cycle on Mars is significantly more pronounced than on Earth, particularly during the solstices. At these junctures, both planets are oriented such that one pole is continuously exposed to solar radiation, resulting in the summer pole absorbing the maximum solar energy throughout the day. On Earth, the thermal inertia of ice and oceans and the reflective properties of ice and snow prevent the North Pole from attaining higher temperatures than, for instance, Viking 1, the inaugural extraterrestrial weather station. Mars temperature is recorded by Viking and relayed directly from Chrysoplanitia. These instruments recorded temperature, wind speed, and pressure at a height of 1.6 meters above the ground from July 1976 to August 1979. Following the onset of northern autumn, refer to diagram, the average temperature gradually declined until the winter solstice. The abrupt occurrence of 2 global dust storms significantly reduced the amplitude of daily temperature fluctuations. During the day, The suspended dust obstructed sunlight, while at night it emitted infrared radiation, thereby restricting surface cooling. This phenomenon resembles the impact of clouds on Earth. Temperatures are more moderate under overcast skies compared to clear skies at night. Death Valley in California experiences negligible effects on Mars, where temperatures, averaged daily, peak in the polar region of the summer hemisphere during the solstice. Temperature consistently declines from the summer pole to the winter pole. Conversely, a more familiar scenario emerges during the Martian equinoxes: frigid polar regions and warmth near the equator. The Martian atmosphere. Until the 1960s, Mars' atmosphere was presumed to be nitrogen akin to Earth's. Astronomers relied on accurate measurements, but overlooked the influence of dust, which creates the optical illusion of a dense Martian atmosphere. Consequently, they were astonished when, in 1965, Mariner 4 transmitted signals through the atmosphere while passing behind the planet, revealing its tenuous nature and indicating that the mean surface pressure on Mars was approximately 6 hectopascals, equivalent to Earth's pressure at an altitude of about 30 kilometers. Mars's atmosphere comprises 95% carbon dioxide, which is toxic to humans. Survival at such low pressure necessitates a pressurized spacesuit. The primary components of the atmospheres of Mars and Earth. We are analyzing the mean temperature profiles of Earth and Mars. The lower few kilometers of both planets encompass most of the atmosphere's mass. In this well-mixed layer, the troposphere, temperature decreases rapidly with altitude. A substantial ozone layer warms Earth's atmosphere between 20 and 60 kilometers due to ultraviolet radiation absorption. Conversely, Mars possesses a negligible ozone layer. Instead, the thermal profile stabilizes between 60 and 120 kilometers, due to the absorption of near-infrared solar radiation. Above 120 kilometers, in the thermospheres of Mars and Earth, the sparse molecules are impacted by intense ultraviolet radiation, resulting in their fragmentation and increased temperature. The thermosphere's temperature exhibits significant daily and seasonal fluctuations and is influenced by solar eruptions. The Viking missions 1976 determined the other main components of the Martian atmosphere. In situ measurements confirmed the presence of the transparent and neutral gases, nitrogen and argon. Traces of oxygen, O2, exist in negligible quantities compared with the oxygen content of the Earth's atmosphere, resulting from photosynthetic activity in plants and bacteria. So, on Mars, oxygen derivatives, such as ozone, O3, produced by photodissociation in the ultraviolet rays of the sun, are rare. Such a small amount of atmospheric ozone offers no protection from ultraviolet radiation. Mars has no ozone layer. Therefore, this radiation can dissociate atmospheric CO2 into oxygen, O2, and carbon monoxide, CO, molecules. Why Mars carbon dioxide has not all been thus converted has long been a subject of debate. As far as we know, the small amount of water vapor in the air, see pages 149-151, provides the reactive agent OH, which causes CO to quickly oxidize, recombine with O2 to form CO2. This ensures that carbon monoxide and oxygen remain smaller than carbon dioxide, see table opposite. Mars Express and its SPI-CAM spectrometer, capable of measuring amounts of ozone and water vapor, have increased our knowledge of this atmospheric chemistry. Another spectrometer, PFS, surprised researchers by detecting traces of methane, CH4. Researchers asserted that this discovery pushed the instrument to its limits, but subsequent, and equally challenging, spectroscopic observations from Earth validated this. Methane's instability in the Martian atmosphere necessitates the presence of a subsurface source, which could be evidence of ongoing volcanic activity. Could there be evidence of life existing underground? Low ground? What causes winds on Mars and Earth? Two primary factors interact. Thermal differentials. Temperature differentials induced by solar radiation are the primary catalyst for atmospheric dynamics. Warm air expands and ascends, increasing air density at lower altitudes relative to surface pressure. Consequently, thermal disparities generate pressure gradients at altitude, propelling air masses from regions of elevated pressure, warmer areas, toward regions of diminished pressure, cooler areas. This phenomenon manifests as winds. The Martian atmosphere exhibits significant thermal variations. The illustration depicts average atmospheric temperatures during the winter solstice in the northern hemisphere, expressed in degrees, as recorded by the TES spectrometer on the Mars Global Surveyor. The warmer air of the summer hemisphere possesses a lower density than the colder air of the winter hemisphere. Consequently, at higher altitudes, the summer air is displaced towards the winter hemisphere. Warmer regions induce meridional, north-south circulation, which transports air masses toward cooler regions at altitude, where they cool and descend. Subsequently, the air masses cool and descend further. The lower atmospheric layers then redirect the air masses back toward warmer regions. This phenomenon on Earth is termed Hadley circulation, named after the English physicist who first elucidated the process in 1735. The atmosphere forms pairs of cells around the planet, between the intertropical zone and each hemisphere. In contrast, Mars typically features a single extensive Hadley cell that spans both hemispheres and straddles the equator. Additionally, the Martian cell is significantly more pronounced at altitude than its terrestrial equivalents. On Earth, Hadley circulation is restricted below the stratosphere, inhibiting vertical circulation. However, this limitation does not apply to Mars, as it lacks a stratosphere. Winds in the Martian atmosphere are generated by meridional circulation and the planet's rotation. On a rotating planet, meridional south-north air movements produce strong lateral easterly or westerly winds that dominate atmospheric circulation. This occurs because near the surface, at the base of the ascending branch of the Hadley cell, air follows the planet's rotational axis. As the air is drawn towards the equator in the upper cell, it moves away from the axis of rotation. Like a skater extending her arms while spinning, these air particles rotate more slowly than the planet, resulting in retrograde winds that blow from east to west. As they approach the pole, the air masses near the axis of rotation begin to rotate faster than the planet, akin to a skater pulling in her arms, forming a strong westerly jet around the pole, comparable to the terrestrial jet stream. A similar process occurs at lower altitudes. Planetary rotation also influences air movements. Planetary rotation also affects air movements. D. Mars has almost identical rotation periods and similar seasonal variations in insolation. The red planet exhibits meteorological elements unlike Earth. So, Mars has its westerly winds at around 50 degrees, a jet stream, like the high-altitude currents circling the Earth from west to east at mid-latitudes in both hemispheres, tropical trade winds, etc. At least, that is what we deduce from the scarce data provided by infrared detectors and the Viking landers. Computer models of the Martian atmosphere help us analyze and interpret these data. Such studies also reveal fundamental differences between atmospheric circulation patterns on Earth and Mars. The absence of oceans on Mars is a factor here. On Earth, the lower layers of the atmosphere are generally warmer in the tropics than at the poles. While on Mars, for most of the year, the thermal contrast is between the spring-summer warm hemisphere and the autumn-winter cold hemisphere. This phenomenon is due to the hypercontinental nature of the Martian climate. Although, around the equinoxes, a more Earth-like situation pertains, and it is colder at the poles. In addition, the contrast in temperature between the hemispheres is heightened because of dust in the atmosphere, which absorbs solar radiation directly in regions where insolation is greatest. To a specialist in Earth's climate, a meteorological chart of Mars may not appear as extraterrestrial as one might expect. The prevailing wind patterns are analogous on both planets. For instance, at Europe's latitude, winds predominantly originate from the west, influenced by the cyclical movement of high-pressure systems, anticyclones, and low-pressure systems, depressions, that alternate weekly during autumn and winter. A chart depicting mean surface. Winds on Mars during the northern winter solstice, produced by a computer model at the Laboratoire de Météorologie Dynamique in Paris. At latitudes comparable to Europe, 35-50,075 BUSN, the Martian jet stream exerts a surface influence akin to Earth's. The winter winds on Mars predominantly exhibit a westerly direction, A, particularly at elevated terrains. Further south, the return branch of the Hadley cell impacts both hemispheres in the lower atmospheric layers. Deflected by the planet's rotation, it generates easterly trade winds north of the equator between 0 degrees and 30 degrees and B, intensifies upon crossing the equator, and subsequently induces robust westerly jets, reminiscent of summer monsoon winds in India and Central Asia, around 30 degrees C. Wind streaks are present on the surface. Annually, light-hued dust accumulates in the lee of obstructions like minor craters, signifying the direction of the dominant wind. These deposits are discernible in regions with darker terrain, particularly in two locations adjacent to Alcides Planitia on either side of the Martian equator, illustrated as white rectangles on the wind chart. In the tropical latitudes of Mars, a trading system and monsoon winds are similar to those on Earth, characterized by a predominantly continental climate, specifically resembling that of Asia. Upon closer examination, the meteorologist will observe that Mars exhibits a hypercontinental climate, resulting in intensified diurnal wind oscillations due to significant temperature disparities between day and night. This phenomenon is less pronounced on Earth. During nighttime, the atmosphere near the Martian surface becomes exceedingly cold, causing denser gas to flow down slopes and generate strong localized winds until dawn. Conversely, in the afternoon, the warmed air near the surface ascends slopes. All Mars probes have consistently documented these pronounced oscillations. Temperature and wind variations near the Martian surface indirectly affect all atmospheric layers. Diurnal temperature and wind oscillations transmit diurnal frequency waves occurring once daily, or semi-diurnal frequency waves, occurring twice daily, akin to ocean tides, hence termed thermal tidal waves. In conjunction with other winds, these diurnal oscillations significantly influence atmospheric circulation on Mars and pose complex theoretical challenges for aspiring Mars meteorologists. The solid particles on the Martian surface vary from a few micrometers in diameter, dust, to hundredths of a micrometer, sand. The wind can elevate and transport the finest particles, resulting in dust storms. See the following pages. This process, known as saltation, displaces them from the ground. Over time, as winds persist, sand and dust accumulate to create particularly abundant dunes on Mars. Mars features both linear dunes and Bartians. Dunes on the planet can be either linear or crescent-shaped, Bartians. The leeward flank accumulates material, leading to future avalanches that steepen that flank. Dunes are prevalent across Mars, akin to the ergs found in terrestrial deserts. These formations are commonly located in valley bottoms and low-lying regions. Although we have not yet observed such movement, most of these dunes are believed to undergo gradual displacement over time. Imagery from Viking and Pathfinder distinctly illustrates that numerous Martian rocks have been eroded by wind-driven particles. with their surfaces displaying striations and centimeter-sized pits resulting from this abrasion. Due to Mars's scant atmosphere, wind erosion may not significantly influence the planet in the short term. Nevertheless, the wind's erosive activity will substantially impact exposed rocks over millions or billions of years. The dust cycle, perpetually orange skies, and an atmosphere saturated with dust. Mars's initially perceived grey-blue sky was later recalibrated to reveal its true and surprising colours: russet, orange, and salmon pink. This phenomenon is attributed to 1 micrometer diameter mineral dust particles suspended in the atmosphere. Can the most powerful winds, undetectable to future Mars astronauts, elevate and sustain substantial quantities of dust? Currently, there is no definitive answer to this inquiry. Wind tunnel experiments replicating Martian conditions have demonstrated that winds reaching 100 km/h velocities can displace particles approximately 100 micrometers in diameter. These particles subsequently mobilize finer dust, capable of remaining airborne for extended periods, before eventually settling, a process known as sedimentation. Precipitation events, such as rain and snow, routinely eliminate this fine dust. Such a phenomenon may occur on Mars, albeit with significantly reduced efficiency. Suspended dust induces significant fluctuations in atmospheric opacity, resulting in notable variations in average air temperature. Even in relatively clear Martian conditions, the temperature at an altitude of 20 km is 30 degrees, higher than in the complete absence of dust. During dust storms, this temperature can reach 80 degrees Celsius. Such variability is absent on Earth. During the day, Martian dust absorbs solar radiation, heating the upper atmosphere while cooling the surface. Conversely, at night, infrared emissions from the dust warm the surface. Consequently, dust mitigates the temperature differential between day and night, although it does not substantially affect mean surface temperatures. The dust cycle. Planet of storms. The dust cycle. A planet characterized by storms. Numerous dust storms traverse Mars daily. Localized storms, everyday events on Mars, and space probe observations raise most dust in the Martian atmosphere. Most of these events are associated with atmospheric low-pressure areas in high and mid-latitudes or around the edges of the seasonally changing ice caps, where temperature contrasts between the carbon dioxide snow and the ice-free surface engender strong thermal breezes. Every year, dozens of Martian storms attain regional importance, extending across thousands of kilometers. They may last for several days, especially in southern spring and summer. Observations of atmospheric dust tell us that the year can be divided into 2 distinct periods: a clear season during northern spring and summer, and a dust season, when severe storms occur, during autumn and winter. In the clear season, storms are relatively few, and there is not much dust in suspension in the atmosphere. One clear season resembles the next. Typical small storms arise on similar dates, and the usual quantities of suspended dust are observed. However, the major meteorological events characterizing the dust season vary yearly. In some years, 1 or more truly global storms may shroud the Martian surface for months. The TES spectrometer on the Mars Global Surveyor quantifies the variation in dust concentrations within the Martian atmosphere relative to latitude. A pristine atmosphere is depicted in violet, while a dust-heavy atmosphere is represented in red. The occurrences during the season of massive storms exhibit significant annual variability. For example, 1999, only a few regional dust storms were recorded, whereas a global storm persisted for several months in 2001. The data distinctly illustrate dust elevation in localized storms surrounding the edges of the seasonal polar caps. The caps appear white due to the inability to conduct infrared dust measurements at low temperatures. Violent winds at the periphery of Mars's seasonal polar carbon dioxide cap generally induce dust storms. The Mars Global Surveyor documented one storm near the northern polar cap in August 2000. Spanning approximately 900 kilometers, it resembles a Saharan dust storm that transpired a few months prior on Earth. The structural characteristics in both instances are analogous. At the rear, a central jet sustained by the storm, with a confined zone of activity, and at the front, a mushroom-shaped front of dispersing dust. The dust cycle. Vortices of dust. Observations from Viking in the 1970s and from later probes such as Pathfinder, Mars Global Surveyor, and Mars Exploration Rover revealed that atmospheric dust on Mars is also lifted in the form of vortices commonly known as dust devils. Researchers believe these events may be much larger than anything we see on Earth based on their shadows on the ground, which are easier to see than the dust columns. Martian dust devils may reach 10 kilometers in height, some tens of meters, or even hundreds of meters in diameter. On Mars, they occur in the afternoon when surface temperatures are highest and atmospheric convection is strongest. A dust devil draws in surrounding air and concentrates it at its center. According to the same principle as that which makes ice skaters rotate faster as they pull their arms inwards, the masses of air sucked in towards the dust devil's axis of rotation are strongly accelerated, resulting in violent transverse winds. Combined with the vertical aspiration at the center of the dust devil, these winds lift large quantities of dust. We still need to discover the exact proportion to which these dust devils contribute to the dust supply in the Martian atmosphere. One highly visible feature of the planet's surface is the innumerable graffiti scored across it for enormous distances by dust devils. See images below and on the facing page. The ground that a dust devil has cleaned typically appears darker than the fine dust surrounding it, making these tracks simple to see. The dust cycle. Planetary storms. When the entire globe vanishes beneath dust. In the summer of 2001, a colossal dust storm emerged on Mars during the final days of June. Originating near the southern polar cap and advancing towards Hellas, it traversed approximately 4,000 kilometers in 2 days, crossing the equator and instigating dust upsurges in various regions. The planet remained obscured by dust until the end of September, as depicted in the 2 upper images from the Hubble Space Telescope provided by NASA. Subsequent analysis of the observations indicated that this phenomenon was not a truly global event, but rather a series of localized occurrences, with dust being actively raised in specific areas. How does a local dust storm become a planet-wide event? The mechanism is as yet poorly understood. What we do know is that the lifting of dust into the atmosphere causes considerable meteorological changes. By absorbing the sun's rays, the dust warms the atmosphere locally, creating or increasing temperature differences, the driving force behind winds and atmospheric circulation. On the global scale, a little dust lifted into the tropical atmosphere of Mars' southern hemisphere, where many local dust storms occur during summer, intensifies the circulation within the Hadley cell and, thus, the trade winds. See pages 128, 133. Models show that this strengthens the winds, especially in the southern tropics. These winds pick up more dust, and the dust causes stronger winds. The machine fuels itself. This kind of mechanism also operates on a local scale. A combination of local and global phenomena likely triggers global storms. In light of these facts, why do such storms occur in some years and not others? The answer is still elusive. Each southern spring, when Mars approaches its perihelion and insolation reaches its zenith, numerous local and occasionally regional dust storms manifest in the southern hemisphere. In certain years, one or two storms may escalate into an extraordinary meteorological phenomenon unparalleled in the solar system: a global dust storm. This event resulted in dust enveloping nearly the entirety of Mars for several months. In 1956, astronomers observed the first events when Mars was closer to Earth than usual. Astronomers were surprised by the extent of the phenomenon and disappointed at being unable to see anything through it. The famous American popularizer and champion of astronomy, Carl Sagan, wrote that at the time, Mars was about as fascinating as a baseball with no seams. The phenomenon was recorded again in 1971 as the American probe Mariner 9, and then two Russian probes, Mars 2 and Mars 3, went into orbit around the planet. They were witnesses to the most intense global dust event ever seen. As the dust began to settle, Mariner 9 was still operating and managed to secure photos of the surface. See pages 187 to 89. During the next Martian year, 1973 on Earth, another planet-wide storm occurred, and no less than 100 days apart, were unleashed during the first year of Viking's 1977 mission. There were no similar events during the next 2 Martian years. But in Viking's fourth year, 1982, they recorded another global dust storm. Nearly 20 years had passed since the next event, when the Mars Global Surveyor told us about a new global storm. The 1970s saw the greatest concentration of such storms, as recorded between 1956 and the present. Why should that decade be so exceptional? The answer may depend on how astronomers observe the planet and space missions, rather than climatic anomalies. As it happens, 1971 and 1973 were years of better visibility during the storm season, as was 1956. Resolution was good. The geometry of the two planets' orbits lends itself to more favorable observations at intervals of about 16 years. The hydrological cycle, vapor, frost and ice, water on Mars. The Martian atmosphere conveys water in the form of mist and clouds. Despite the absence of oceans or canals, Mars retains considerable water, demonstrating a seasonal hydrological cycle. The TES spectrometer aboard Mars Global Surveyor monitored the yearly water vapor cycle. The water vapor concentration in Mars's atmosphere is depicted as a function of seasonal time and latitude, quantified in precipitable micrometers, representing the depth of liquid water that would accumulate if all atmospheric water condensed on the surface. The enduring northern polar cap, an extensive glacier composed of water ice, sediments and dust, characterized by sinuous troughs. Provided by NASA JPL, Malin Space Science Systems. Spanning over 1,000 kilometers, the cap is enveloped in a layer of relatively pure white water ice that interacts with the atmosphere. Seasonal warming generates atmospheric water vapor. These interactions have sculpted its surface into a topography of pits, bumps, and knobs, approximately 20 meters wide and 2 meters deep. All phenomena originate at the North Pole. Over time, a substantial glacier composed of water, dust, and sediments has developed. During the summer, solar radiation warms its frigid surface. The ice does not liquefy, as the atmospheric pressure on Mars is insufficient to permit water to exist in a liquid form. Rather, it sublimates directly into the atmosphere. For several months each summer, atmospheric circulation redistributes water vapor from the northern polar region to various latitudes. The amount of water involved is not great. If all the water in the Martian atmosphere fell to the surface, there would be enough to form only a few tens of micrometers of ice in the wettest regions. Despite the comparative lack of water in the atmosphere, saturation is often reached at such low temperatures that clouds form, and frost can appear at the surface. Water vapor can also diffuse into the porous regolith, forming the planet's uppermost layer. This set of processes represents Mars' water cycle. The essential question is whether the cycle is closed. Does the water periodically return to its initial state as ice in the North Polar Cap? And the reply is yes, but for there exists on Mars an area where water condenses but never leaves, the South Pole. This is due to a layer of carbon dioxide ice permanently covering the southern polar cap. See pages 164-166. The surface here is at such low temperatures, 130 degrees, that any water present will exist only as ice. The ice cap locks water in a veritable deep freeze. So the long-term water cycle on Mars seems to be a one-way journey, transporting water from the north to the South Pole. Mars could not have maintained this dynamic throughout its history. The North Pole would have no water. It is very probable that at some time in the past, the cycle operated in the opposite direction. The hydrological cycle. Clouds and mist. Insipid clouds, devoid of precipitation. Clouds are integral to meteorology and climate on Earth. They emit heat during condensation, when water vapor transforms into clouds, and serve as a substantial energy source in the dynamic atmosphere. Conversely, their radiative properties, the ability to reflect or absorb radiation, significantly influence the planet's energy balance. The conditions on Mars are markedly distinct, characterized by lower temperatures, pressures, and water availability. Nonetheless, Martian clouds remain a focal point for planetologists, as diverse cloud formations play a crucial role in Martian meteorology. Notably, the minute ice crystals, measuring 1 to 5 micrometers, that form these clouds will sublime before reaching the surface. Their descent velocity and aggregation rate are insufficient for precipitation to occur on Mars. In which locations on Mars are clouds observed? Nearly every year, from late spring through summer in Mars's northern hemisphere, a belt of clouds, observable from Earth, encircles the Martian equator. This foggy phenomenon originates from the northern polar ice cap, where significant amounts of water vapor are emitted into the atmosphere, characterized by its coldness due to minimal dust presence. The ascending limb of the Hadley cell swiftly conveys this water vapor to tropical latitudes. As it ascends, it encounters progressively colder air strata, until it attains a saturation threshold, at which point it condenses. The Martian cloud belt parallels the intertropical cloud belt on Earth, with its intermittent presence resulting in rainy seasons. The autumn and winter seasons induce significant air cooling in the polar areas. As the air mass advances toward the poles, it condenses, manifesting diverse cloud formations, some dispersed and others distinctly structured. Astronomers designate this phenomenon as the polar hood. It is particularly prominent in the northern hemisphere and far more diffuse in the southern hemisphere. The carbon dioxide cycle. Seasonal polar ice caps. A layer of carbon dioxide frost. With the onset of spring in either hemisphere, the resurgence of daylight following months of polar night unveils a stunning spectacle. From the pole to latitude 50 degree, the Martian surface is adorned with a radiant frost layer that progressively retreats poleward as the new season advances. Upon their initial observation of the seasonal polar ice caps in the 17th century, astronomers were unequivocal in their conclusions. The image illustrates the northern polar cap in mid-spring. This is a photomosaic composed of photos captured by the Mars Global Surveyor at approximately 14-town local time in July 2002. A portion of the cap would consistently reside on the planet's nocturnal hemisphere. The seasonal caps comprise a layer of carbon dioxide ice ranging from 10 cm to 1 nemeter thick, accumulating during autumn and winter and gradually transitioning to gas, sublimation, in spring. The cap measures merely 3,000 kilometers in width, reduced from its midwinter diameter of 5,000 kilometers. The yearly polar caps additionally encompass a minor quantity of water ice in crystalline structure. In spring, along the periphery of the caps, this water ice sublimates more slowly than the carbon dioxide. This elucidates why snow and frost accumulations resemble those on Earth. It was not until 1966 that their true composition was unveiled, as the examination of data from the inaugural Mars spacecraft, Mariner 4, disclosed that they consisted of frozen carbon dioxide and dry ice. In the polar areas, during autumn and winter, temperatures decrease until they reach the condensation point of carbon dioxide. On Mars, this transpires at approximately 125 degrees Celsius, with the value contingent upon atmospheric pressure. The atmosphere condenses, depositing snow and carbon dioxide ice on the ground. In spring, the solid carbon dioxide will once more sublimate, transitioning directly to the gaseous form without liquefaction. In the northern hemisphere, the seasonal CO2 layer gradually diminishes throughout spring, ultimately vanishing by the onset of summer. The permanent ice cap at the North Pole becomes apparent when it melts and remains visible until carbon dioxide reappears in the subsequent autumn. In the southern hemisphere, the winter retreat is less consistent, with CO2 concentrations diminishing in certain locales while remaining stable in others at the same latitude. Adjacent to the South Pole lies an area where carbon dioxide never fully sublimates. This residual cap signifies a permanent repository of frozen atmospheric gas, a phenomenon unparalleled on Earth. The CO2 cycle, an environment that consolidates CO2. The date is April 1998. The planet is undergoing its northern winter season. Following extensive months of maneuvering, the Mars Global Surveyor has finally directed all its equipment toward the planet's surface. The Molar Laser Altimeter assesses topography with an accuracy of a few meters. It unexpectedly uncovers buildings over 10 kilometers in height, dispersed beneath the Arctic night, which have never been identified before. It soon becomes evident that these clouds manifest exclusively without light. The atmospheric theoretical models indicate that these clouds consist of solid carbon dioxide, distinguishing them from other Earth clouds. Initially, elucidating their production seems uncomplicated. As the temperature decreases to 125 degrees, the condensation point of carbon dioxide under Martian low-pressure circumstances, the atmosphere freezes, resulting in the formation and aggregation of particles into clouds. Nevertheless, the many aspects of this process are not readily apparent. These clouds markedly differ from their typical Martian or terrestrial water-based equivalents. The quantity of water vapor present in the atmosphere constrains the dimensions of droplets in aqueous clouds. Carbon dioxide clouds have an abundant supply of CO2, constituting the Martian atmosphere's primary component. When a portion of the atmosphere is swiftly cooled, such as when the wind encounters topographical relief and ascends into colder strata, the Martian surface undergoes genuine CO2 blizzards. The descending snowflakes enhance the substantial quantities of carbon dioxide ice that have solidified directly on the surface. Whether northern or southern, the yearly polar cap generally retains approximately 30% of the atmosphere. This condensation sublimation process has worldwide implications. Initially, it generates a CO2 flow that transfers from the sublimating cap to the condensing cap. This constitutes a significant aspect of atmospheric movement on Mars. Secondly, it induces seasonal fluctuations in the atmosphere's overall mass, influencing the planet's surface pressure. A portion of the atmosphere condenses at the polar caps, inducing fluctuations. Viking 1's data indicated 2 minima throughout the southern and northern winters, when the atmosphere partially freezes on one of the polar caps. Pressure decreases in the southern winter due to the condensation of more CO2. The eccentricity of Mars's orbit results in a longer southern winter than the northern winter. Can CO2 ice clouds be located on Mars? Carbon dioxide clouds develop not solely during the Arctic night. The whitish layer, observed at an altitude of 100 kilometers by the Mars Global Surveyor, may consist of suspended small particles of solid CO2. Courtesy, NASA, JPL, Marlin Space Science Systems. Temperature profiles, left, obtained by the Pathfinder mission in 1997 and monitored by the SpyCam instrument on Mars Express, indicate that the high-altitude atmosphere may attain the condensation point of CO2, even in tropical regions during summer. SPLCAM's findings revealed that very thin clouds develop in regions with extremely low temperatures. Frequently, spectrometers cannot directly analyze these clouds due to their tenuous composition. The Omega imaging spectrometer aboard Mars Express has detected alterations in the atmospheric radiation. Ice particles composed of carbon dioxide suspended in the atmosphere induce these alterations. The CO2 cycle. The fluctuations of carbon dioxide ice. Carbon dioxide snow sublimates throughout the spring on the dunes of the southern hemisphere. The dark blotches on the ice are believed to consist of sand and dust, propelled by strong jets of carbon dioxide gas that emerge as the ice begins to sublimate in early spring, as the sun ascends above the horizon. Researchers analyzing data from NASA's Mars Odyssey orbiter report that each spring is marked by explosive eruptions near Mars's south polar ice cap. In this depiction, dust-filled jets ascend into the Arctic atmosphere. Under the vernal sun, the snow-covered terrains of Martian high latitudes are among the most stunning and unique in the solar system. Satellite imagery of the polar caps has unveiled enigmatic structures, but the origins and development remain unclear. Envisioning the configuration of the ice mantle from approximate viewpoint is tough. Martian snow and ice likely contain few entrapped air, CO2 bubbles upon condensation, as the air itself undergoes condensation. Carbon dioxide ice likely forms dense, uniform, and nearly transparent layers in certain locations. As the spring sun radiates, any minuscule particle of dust embedded in the translucent ice will absorb energy, increase in temperature, and perhaps envelop itself in a gas bubble as the ice undergoes sublimation. The sun may also heat the stony substrate beneath the ice, resulting in sublimation from below. In certain regions, springtime ice may exist in a state of levitation, supported by a cushion of pressurized air. Should a fissure develop in the ice layer, driving forces beneath may induce a substantial eruption of gas and dust onto the ice cap's surface. Polar arachnids. In specific regions near the South Pole, geysers of carbon dioxide and dust erupt from the cap during spring. They can be recognized by the dust they disperse downwind in their surroundings. This gas likely emanates from the melted ice beneath, propelled by solar radiation, heating the underlying rocks, allowing the gas to permeate the transparent ice. As the gas propels forward, its movement beneath the ice appears, forceful to wear away the surface and transport mineral particles over several tens of meters. The local topography dictates the sites of these geysers, resulting in consistent erosion at the same locations annually. The rocks and soil in these regions exhibit stair-step erosion patterns over time. These figures can be observed beneath the ice surrounding the sites of active geysers in the spring. They become more discernible in the summer, when the carbon dioxide ice fully vanishes. Illustration attributed to S. Pico. Source: NASA, JPL, Marlin Space Science Systems. The carbon dioxide cycle, the remaining southern polar cap, a repository of frozen atmosphere. While all remnants of polar CO2 ice vanish in the northern hemisphere throughout summer near the South Pole, the seasonal sublimation of CO2 snow reveals a persistent layer of solid carbon dioxide in equilibrium with the environment. Paradoxically slender. This enduring deposit perplexes planetologists due to its remarkably thin nature. Merely a few meters at most, equivalent to several years of seasonal condensations. Ultimately, this glacier is expected to vanish or develop into a more significant mass, amassing more ice. The ice cap cannot naturally stabilize between these choices unless an unidentified feedback mechanism maintains equilibrium. An alternative hypothesis posits that the residual southern cap periodically arises in response to climatic fluctuations in the CO2 cycle, which transpire over decades. Nonetheless, the occurrence of such phenomena remains speculative. The photograph depicts a slender coating of carbon dioxide ice on a water ice base. This false color montage consists of photos captured during the southern summer by the Omega mapping spectrometer on Mars Express in 2004. Omega can differentiate between water ice and carbon dioxide ice using infrared spectroscopy. A thin layer of pale pink carbon dioxide ice overlays the blue water ice, extending for several meters. What accounts for the presence of a remnant ice cap exclusively in the southern hemisphere? No permanent CO2 cap exists at either pole, which is expected as such a cap would develop where CO2 ice is most stable, specifically in the coldest regions. The present orbital eccentricity of Mars results in a shorter southern summer, despite its increased warmth, compared to the northern summer. This may result in increased stability of ice near the South Pole. This scenario developed throughout the years. One might envision the contrary condition tens of thousands of years ago, where the northern ice cap was saturated with CO2 and its southern counterpart emitted water vapor. The planet's orientation to the sun dictates its climate. A planet's climate is influenced by changes in its orbital characteristics, especially its obliquity, which is the angle between the axis of rotation and the perpendicular to its orbital plane. The fluctuations in Earth's obliquity, however small due to the stabilizing influence of the Moon, have had a role in glaciations. Recent studies indicate that Mars has seen a tumultuous series of fluctuations in its obliquity, exhibiting a pseudo-period of approximately 100,000 years, with extreme values ranging from 0 degram to over 60 degram. Mars, with a present obliquity of 25.2 degram, has a history of significant climate fluctuations. What is the essence of these variations? When the obliquity is minimal, 0 degree to 20 degree, seasons are less distinct. The poles, characterized by less extensive seasonal CO2 ice caps, get diminished energy on average due to the sun's consistently low position in the sky. Temperatures in polar regions are lower. Consequently, the proportion of the atmosphere is likely perpetually maintained as CO2 ice, now at the South Pole, refer to preceding pages, rises. Consequently, the atmosphere is less dense. This research investigates the impact of obliquity on the climate of Mars. A. Low obliquity, 0 degree to 20 degrees. B. High obliquity, 27 degree to 40 degrees. C. Very high obliquity, 40 degree to 60 degree. Several million years ago, glaciers were present in the tropical regions of Mars. Structures akin to specific deposits created by substantial glaciers on Earth are located on the western slopes of the colossal Martian volcanoes in the Tharsis area and surrounding plains, shown in yellow on the map. The extensive Martian glaciers have nearly all disappeared at this point. Nonetheless, the HRSC camera on Mars Express identified a rock glacier, A, in proximity to the scarp of Olympus Mons. This glacier, consisting of ice enveloped by boulders and sediments, mimics those seen in the Antarctic dry valleys. B. Regions akin to Mars, notably frigid and arid. How could glaciers have developed on a planet where surface ice is only stable at the poles? Computer simulations of the Martian environment during periods of elevated obliquity indicate that the atmosphere contained significantly more water vapor than it does currently. Westerly winds propel this humid environment onto the volcano's slopes, resulting in rapid cooling. Ice precipitated and descended to the surface. Estimates indicate that the accumulation rate was roughly several millimeters a year, adequate to generate a glacier over millennia. Although most of the water has evaporated, a tiny quantity of ice may persist at the core of the rocky glacier, shielded by its protective coating of rocks and dust. When the obliquity exceeds 27 gra, the seasons are more pronounced. Increased yearly mean insolation at the poles results in greater temperature at deep. The pores of the Martian subsoil release stored CO2 ice, referred to as adsorbed carbon dioxide, until the reservoir is depleted. The capacity of this reservoir is indeterminate. However, one can envision an atmosphere with double the density. Circulation in this atmosphere would amplify as seasons become more pronounced. We could elevate and sustain substantial volumes of dust in suspension. During summer, the polar ice storage would experience significant warming, resulting in a substantial release of water. The hydrological cycle, encompassing clouds and frost, would be markedly more dynamic than currently observed. Glaciers develop when obliquity surpasses 40 degrees. Computer simulations of the Martian environment indicate that warming any remaining polar ice would release a substantial volume of water into the atmosphere, resulting in water vapor condensing and precipitating more quickly than it could sublime in specific regions. In these regions, ice would have amassed, if there remained a supply at the pole, and might have potentially given rise to glaciers. The remnants of these glaciers have been located in areas predicted by models, specifically on the slopes of the colossal Tharsis volcanoes and to the east of the Hellas Basin. Prehistoric glaciers on Mars. Structures analogous to glaciated valleys on Earth. Before the predictions made by computer models on the formation of glaciers on Mars due to alterations in the planet's orbital parameters and axial tilt, scientists had previously discovered evidence of glaciers in specific locations. For instance, at the interface between the cratered highlands and the lower northern plains, there are extensive valleys of 5 to 10 kilometers in width and 1,000 meters in depth, characterized by a distinctive morphology. Their level surfaces are marked in the direction of the valley's orientation. These score marks, characterized by alternating ridges and crevasses, originate at the valley walls and curve inward to conform to the longitudinal slope of the valleys. They provide evidence of a composite of ice and rocks that formerly exhibited flow akin to glaciers on Earth. Rock debris from the valley walls created moraines transported by the glaciers. While the ice has vanished in other valleys, the erosion markings resemble those observed in old glaciated valleys on Earth. This indicates that a sheet of ice around 1 kilometer thick has worn away the surface. Considering Mars's reduced gravity and the mild gradient of the valleys, the ice must have been a minimum of that thickness to initiate glacial movement. What mechanisms could have led to the formation of these glaciers under the atmospheric conditions present on Mars? Airborne precipitation was not the sole contributor to the formation of all these historic glaciers. In certain instances, water is released from a pressurized subterranean reservoir, and upon reaching the surface, it flows and then freezes. Ice cover at elevated latitudes. Above latitude 60 degrees, a layer of ice deposited millions of years ago lies beneath the surface. In October 2001, Mars Odyssey, which had recently arrived to join Mars Global Surveyor in orbit around the planet, was equipped with novel sensors. One of these instruments was the gamma-ray spectrometer, operating with neutron detectors. Neutrons are particles that, along with protons, constitute atomic nuclei. The neutron detector indicated the existence of subsurface water by monitoring neutron flux on Mars. Subsurface atoms generate neutrons upon interacting with energetic particles, cosmic rays, from many sources. Consequently, detectors on space probes can capture and examine the neutrons that Mars continuously generates. The number of neutrons emitted from a certain area can indicate the existence of ice close below the surface. As these particles must pass through the different subsurface strata of Mars before escaping into space. The hydrogen in water molecules is notably effective in decelerating them during travel, a characteristic of water employed in nuclear reactors. An increase in surface ice correlates with a reduction in neutron flux strength. There was widespread astonishment when Mars Odyssey's sensors relayed data indicating that in specific areas, substantial amounts of water are frozen at the surface to a depth of 1 meter. Findings demonstrate that ice concentrations constitute over 70% of the subsurface material in latitudes over 60 degrees. A genuine layer of ice is likely just a few millimeters beneath the arid surface. Below latitude 40 degrees, ice may be concealed more than 1 meter deep, although Mars Odyssey cannot detect it at that depth. What is the origin of Mars's icy layer? Certain experts endorse the theory that the ice formed through straightforward diffusion into the pores of the upper subsurface material. Many, however, consider it more plausible based on the observed ice concentrations that a covering of ice previously enveloped Mars at mid and high latitudes. This scenario is derived from climatic simulations indicating that when Mars obliquity decreases to low values, as observed today following a phase of high obliquity, water deposited in tropical glaciers does not flow immediately back to the pole. It extends across both hemispheres in the region above 60 degrees, creating a layer of ice and dust several meters deep. When the tropical source depletes, the upper section of this layer will sublime, and the water will migrate towards the pole. It would create a sufficiently dense layer of dust to mitigate the remaining ice loss. Intermittent water currents. Evidence of liquid water is merely a few 100,000 years old. Planetologists concurred that liquid water once flowed across the surface of Mars, although this occurred in the planet's far past, billions of years ago. In 1999, photos from the Mars Global Surveyor disseminated globally refuted this view. In high and mid-latitudes, the probe's MOC camera disclosed systems of gully-like formations with a debris apron at their terminus, likely formed by flowing water in geologically recent epochs. Possibly a few million years ago or potentially more recently. This discovery revived the discussion. Has water lately flowed on Mars? Is it currently flowing, or may it be attributed to alterations? What is the source of these characteristics resulting from the movement of water? It is complex to clarify how water can flow in areas where the temperature is sub-zero and the pressure precludes the existence of liquid water. 3 possibilities are presently being evaluated. Subterranean sources. Certain experts suggest the existence of aquifers beneath the surface, heated by internal energy from Mars. These may intermittently flow at the surface. This scenario fails to adequately account for the dispersion of the flow features, which appear unrelated to any volcanic activity. It fails to acknowledge that these traits exist on isolated peaks and dunes. Does a rotisserie effect occur during periods of significant obliquity? Other planetologists, including 2 current authors, have suggested that the flow features form during significant planetary obliquity periods. Atmospheric pressure would have been sufficiently elevated for water to exist in its liquid state above 0 degree now C. During summer, when the axis of rotation tilts towards the sun, slopes facing the poles are perpetually heated, causing the surface ice or the frozen subsurface to have melted to a certain depth, resulting in subsequent releases. Is melting transpiring beneath the snowpack today? Certain flow characteristics are observable in terrains partially obscured by ice deposits deposited on shaded inclines. Certain researchers have proposed the existence of liquid water moving beneath this ice layer. Third diagram, page 176. What heat source induces the flow of water beneath the ice? Polar deposits serve as indicators of historical climatic conditions. Ice accumulation at the North Pole may provide a record of climatic variations spanning several million years. Stratified deposits at the poles, indicators of historical climates. The larger image depicts the North Pole region, derived from molar altimetric data obtained by Mars Global Surveyor. The vertical scale has been amplified. The deposits measure 2 km in thickness and extend 1,000 km in length. The smaller photos, left, from the Mars Global Surveyor depict layers around 100 km apart. Notwithstanding the distance, identical sequences are observable. A false color image above right reveals layers of ice, dust and sand dunes exposed in a scarp at the periphery of Chasma Boreale, in the core of the polar cap. Mars's north and south poles are enveloped by extensive deposits measuring 1,000 kilometers in width and approximately 3,000 meters in depth. At the North Pole, the accumulated sediments are divided by unusual troughs that follow a spiral configuration. The sidewalls of these troughs disclose the composition of the polar cap. Numerous layers, each less than 10 meters thick, vary between light and dark, contingent upon the ratios of ice and dust contained within. The identical stratification can be replicated for hundreds of kilometers. This indicates a worldwide climatic origin, as several layers are deposited in response to fluctuations in orbital parameters. Similar to how ice cores from Antarctica are utilized to examine Earth's historical climates, these deposits may offer insights into Mars' climatic history. What is the length of this climatic history? If the polar cap gradually expanded following the last significant obliquity, aided by glaciers located further south, then this cap has 5 million years of preserved records. The sediments comprise ice and gypsum. Extensive, shadowy dune fields, whose origin is enigmatic, encircle the frigid deposits of the northern polar area. The Omega mapping spectrometer has lately disclosed that certain dunes harbor an unforeseen mineral. Gypsum, depicted in red in this montage of false color photos. The ice appears white. The concentration diminishes from a location at the periphery of the ice cap. Typically, liquid water generates gypsum, a calcium sulfate. What mechanisms could have allowed liquid water to exist near the pole on relatively recent terrain? The gypsum likely derives from a geological stratum previously altered by liquid water when the cap's edge partially melted. This may have transpired due to the ice being significantly thicker than it currently is. On Earth, we also observe the emergence of liquid water reservoirs beneath glaciers and polar ice sheets. Until the 1960s, Mars was monitored and depicted from Earth, while the duration of a Martian year was recognized in ancient times. The exploration of Mars commenced with the advent of the telescope in the 17th century. Terrestrial telescopic observations remain valuable for monitoring the globe during intervals between space missions or for evaluating new sensors. For instance, with a network of radio telescopes, such as the LRAM interferometer, located on the Plateau de Bure in France. Wind speeds on Mars can be quantified through the Doppler effect of the microwave radiation released by its atmosphere. In 1659, Christian Huygens produced initial sketches of Mars, followed by Giovanni Domenico Cassini, who charted the planet, identified its polar caps, and calculated a Martian day at 24 hours and 40 minutes. Numerous scientists persisted in their observations of Mars. However, significant progress was achieved only in 1777, attributable to telescopes crafted by William Herschel, a musician and organist who emerged as one of the most accomplished astronomers of his era. He is most renowned for his discovery of the planet Uranus in 1781. Herschel quantified Mars's axial tilt, obliquity, and deduced from his observations of the polar cap's expansion and contraction that Mars experiences seasons analogous to Earth's. Herschel deduced that the planet has an atmosphere based on the existence of clouds and how the periphery of the Martian disk obscured stars. During the 18th century, advancements in optical tools enabled astronomers to meticulously map the world and designate names to its darker and lighter regions, identified as seas and continents. A red letter designated the year 1877. Mars was comparatively near to Earth when American astronomer Asaph Hall discovered its two moons, Phobos and Deimos. Giovanni Virginio Schiaparelli, the director of the Milan Observatory, produced charts that are comparable in quality to contemporary ones. He identified several traits, many of which remain in use today. His most notable observations pertain to rectilinear characteristics, which he called canali. Inaccurate translations rendered his channels as canals in English and canaux in French, leading to the conception of their artificial origin. This idea captivated the intellect of the affluent American Percival Lowell, who established an observatory in the Arizona mountains in 1896. He formulated an elaborate explanation, which he upheld until he died in 1916. The canals were constructed by an advanced civilization endangered by drought. As late as 1962, debates on the canal's origin continued to be featured in scholarly journals. The investigation of Mars advanced gradually through the utilization of contemporary astrophysical instruments, including spectroscopes, polariscopes, and radiometers. Since 1896, it has been established that Mars lacks oceans. Henceforth, we shall ascribe the dark patches to plants rather than water. In 1920, research concentrated on the Martian atmosphere, leading scientists to determine that it contained minimal oxygen and water, with just carbon dioxide, identified by 1947. The atmospheric density continued to be a topic of contention until the advent of the space age. What is the optimal time for observing Mars from Earth? Mars attains its closest proximity to Earth every 26 months during its orbit. This is referred to as opposition. Mars is positioned directly opposite the Sun on the celestial sphere, as observed from Earth. Mars is optimally viewed during the 2 months before and after the opposition. Due to the eccentricity of Mars's orbit, its apparent size at opposition will fluctuate, causing the planet to appear twice as large in certain years compared to others. Refer to table. The most advantageous oppositions transpire approximately every 15 Earth years. The successful exploration of Mars commenced on July 14, 1965, when Mariner 4, launched in November 1964, flew past the planet at 9,150 kilometers. Mariner 4 was not the inaugural spacecraft to approach Mars. The Soviet space probe, Mars 1, had previously conducted a flyby of the planet, but Mariner 4 relayed the inaugural photos to Earth. The NASA spacecraft equipped with a camera transmitted 22 images of ancient landscapes in the southern hemisphere of Mars. Disappointment dominated. The lack of canals and Martians and excess craters rendered Mars as desolate as the Moon. Furthermore, indirect examination of the atmospheric characteristics revealed a surface pressure below 7 millibars, significantly more tenuous than anticipated in even the most pessimistic projections. What methods can we employ to access Mars? Spacecraft are launched from Earth into a solar orbit to attain Mars orbit, with the aphelion, the point farthest from the Sun, situated near Mars orbit. This approach reduces fuel usage. Aside from modest trajectory modifications, the motors become inoperative following the initial thrust. Mars and Earth travel at varying velocities, necessitating the launch transpires within a specific launch window of 3 to 4 months before opposition, when Earth is nearest to Mars, overtaking it in its solar orbit. Like oppositions, launch windows transpire every 26 months and endure for a few weeks. A voyage to Mars will require between 5 and 11 months, contingent upon the launch year and the rocket utilized. The Mariner 4, 6, and 7 probes were limited to flybys of Mars prior to entering solar orbits. Subsequent probes may utilize retro rockets to decelerate, achieving either an orbit around Mars or a landing on its surface, employing aerobraking as they traverse its atmosphere. In 1971-1972, interest in Mars was revitalized when NASA employed robust launch vehicles to position twin probes, Mariner 8 and Mariner 9, each weighing 9 to 80 kg, into orbit around the planet. On May 8, 1971, NASA launched Mariner 8. However, due to the Centaur rocket's malfunction, it descended into the ocean. Mariner 9 has shown greater success. Launched 3 weeks later, it became the inaugural artificial satellite of a planet other than Earth. The data collected by Mariner 9 would transform our comprehension of the red planet, exposing its authentic, more dynamic characteristics. Upon Mariner 9's arrival at Mars on November 14, 1971, the planet was experiencing the most significant dust storm ever recorded. The dust storm concealed its whole surface. After the situation stabilized, the probe conducted a comprehensive photographic study of the Martian surface, comprising over 7,000 photos. A newly seen planet revealed volcanoes, canyons, riverbeds, and huge glaciers. Using thermal infrared and ultraviolet observations, Mariner 9 scrutinized the surface, atmosphere, polar caps, and clouds in northern winter and spring. Scientific papers have been utilizing data from this spacecraft for over 30 years. On October 10, 1960, barely 3 years after the first launch of the first artificial Earth satellite, Sputnik 1, the Soviet Union dispatched the first Mars probe into space. Marsnik 1 was designated to conduct a photographic flyby of Mars. Nonetheless, it did not attain Earth's orbit. After 11 years and 8 unsuccessful missions, the Soviet probes Mars 2 and Mars 3 transmitted their inaugural photos of Mars in December 1971. Simultaneously, the USA had already conquered Mars with Mariners 4, 6, and 7, while Mariner 9 further solidified this accomplishment with its accomplishments in 1971. The Soviets were disheartened when the pre-programmed Mars 2 and 3 cameras could not obtain photos of a planet entirely concealed by the enormous dust storm of 1971. The limited photos and scant data obtained by the Soviet probes were inferior to the substantial findings of Mariner 9. In 1973, the Soviet Union capitalized on the 2-year postponement of the Viking program by launching 4 space vehicles in July and August to achieve a significant edge. 2 were orbiters, Mars 4 and Mars 5, while 2 were landers, Mars 6 and Mars 7. Mars 4 and 5, with a mass of around 3,500 kg, were outfitted with a suite of scientific instruments intended to observe Mars comprehensively across all wavelengths. The Mars 6 and 7 landers, weighing a little over 600 kg, were equipped with a suite of meteorological sensors and a mass spectrometer to analyze the atmosphere's chemical composition. We expected substantial findings from the Mars quartet. Unfortunately, the gremlins were prepared to assault. Several weeks prior to the launches, the production procedure of the craft's microchips disclosed defects. The opportunity to rectify this was passed, and the decision to proceed with the launch was made. Mars 4 and 7 strayed from their designated trajectories and became untraceable in space. Mars 6 successfully landed but then lost communication with Earth. Data transferred during descent was also rendered unusable. Mars 5 successfully entered Mars orbit but stopped transmitting after 22 orbits. This compilation of failures resulted in an irrevocable decision. The Soviets discontinued their Mars initiative and redirected their focus towards Venus. The decision proved beneficial, as the Venera missions are the sole endeavors that have landed on Venus and captured images, and analyses of its surface were conducted. The Soviets dispatched more probes to Phobos in 1988 and Mars in 1996. Two missions failed, Phobos 1 and Mars 96, while one succeeded partially, Phobos 2. Did Mars, the red planet, exhibit clear anti-Soviet inclinations? Encouraged by the triumph of Mariner 9 in 1971, NASA aimed to deploy a module on the Martian surface. Engineers at the Jet Propulsion Laboratory, JPL, recognized that, despite the Soviets' success with their flights to Venus, a seemingly more hostile planet, their endeavors on Mars had yielded considerably fewer results. Consequently, NASA's preparations for the Viking missions were thorough. Two identical spacecraft, each weighing 3,527 kg, were launched on August 20th and September 9th, 1975. They comprised a Mariner-type orbiter and a lander exceeding 1 ton in weight. This would represent one of the most intricate and expensive explorations ever conducted by NASA. The preparations proved effective as the 10-month expedition to Mars unfolded seamlessly. Viking 1 successfully achieved Martian orbit on June 19, 1976. The instruments, cameras, infrared radiometers, and water vapor detectors were utilized to identify an optimal landing site. Not excessively elevated, not excessively windy, not excessively inclined, not excessively rocky, not excessively dusty, and not near the pole. Identifying such a site from orbit proved nearly impossible, necessitating a postponement of the landing, initially scheduled to align with the American bicentennial on July 4th. National pride was ultimately fulfilled in 1997 when Mars Pathfinder landed. Viking 1 successfully landed on July 20th, coinciding with the eve of Belgium's National Day, on Chrysa Planitia, at a latitude of 22 degrees N. It narrowly avoided a substantial boulder that could have terminated the mission immediately. Images of Mars, captured from its surface, garnered significant media attention. Nonetheless, the mission's principal objective was to pursue extraterrestrial life. As time progressed, the scientists supervising the Viking studies, see pages 83-85, consolidated their findings. Officially, no life, however, the consensus was absent. Like its counterpart, Viking 2 landed unimpeded, this time on the other hemisphere on the Utopia plain, at a latitude of 48 degrees N. The outcomes of its experiments were identical. Nonetheless, the Viking mission was successful. The anticipated operational lifespan of the modules was 90 days, although they provided reliable service for over 6 years. The final communication with Viking 1 occurred on November 13, 1982. Viking 1 facilitated further orbital and surface investigations on Mars's characteristics. Although Viking did not significantly enhance our comprehension of Mars compared to Mariner 9, it is evident that we owe a substantial portion of the data utilized to the Viking missions. In 1975, the Viking 1 lander and its components were in the assembly phase. The orbiter deployed the Viking 1 lander, C. Before landing, Viking traversed the Martian atmosphere at speeds exceeding 4 km/s, safeguarded and decelerated by its thermal shields. Viking deployed a colossal 18-meter-wide parachute at an altitude of 6,400 meters, appropriate for Mars' tenuous atmosphere. Like the lunar modules, retro thrusters decelerated the lander during the final few hundred meters of its fall, guided by the onboard radar. Before departing Earth, the two probes underwent meticulous sterilization to prevent contamination of Mars per an international treaty established in 1968. A plutonium-based radioactive source supplied energy to the module, which employed a parabolic antenna for communication with Earth, either directly or via the orbiters. The Viking landers were equipped with cameras, essential apparatus for biological studies, meteorological instruments, a mass spectrometer, an X-ray fluorescence spectrometer for chemical analysis, and a seismometer. It is infrequently that a goal is so challenging to achieve. A series of Soviet missions recorded merely 4 partial successes. In 1996, they initiated the final mission, Mars 96. The spacecraft was highly ambitious, with a mass exceeding 6 tons, encompassing 4 landings. Shortly after its launch, the mission lost communication in Earth orbit and descended into the Pacific Ocean near the Bolivian coast. The 9 successful American missions cannot obscure the reality of their 5 significant failures. In 1999, NASA experienced significant setbacks, losing the Mars Climate Orbiter and Mars Polar Lander within weeks, and its 2 Deep Space 2 soil-penetrating microprobes. Launched in the same year, the Japanese Nozomi probe experienced a comparable outcome following an extended trajectory around the Sun. Nozomi's difficulties commenced in 1998, when a defective valve in the propulsion system obstructed its trajectory injection toward Mars. Japanese mission controllers ingeniously created an extended flight plan that would have positioned Nozomi near Mars in late 2003. Nevertheless, a significant solar flare in April 2002 halted the mission, impairing its electrical and heating systems. The spacecraft's fuel freeze incapacitated it, resulting in its loss in December 2003. Nozomi's misadventure was merely one of many. To date, a comprehensive array of potential accidents exist, including 7 failures during the critical launch time. Human mistake significantly contributed to the incident. The Soviet spacecraft Cosmos 419 disintegrated in Earth orbit in 1971 because one of its operators erroneously programmed the insertion from Earth orbit into a Mars trajectory for 1.5 years instead of the intended 1.5 hours. The Mars Climate Orbiter disintegrated upon entering orbit at 57 kilometers instead of the intended 120 kilometers, because one team employed English units, while the other utilized metric units for trajectory correction instructions. A radio blackout might result in unidentified failure causes, as exemplified by the Mars Observer, which was lost shortly before entering Mars orbit in 1993. In 1999 and 2003, the Mars Polar Lander and Beagle 2 entirely disappeared during their descent to the Martian surface. Occasionally, errors result in discoveries. An exemplary instance is the detection of magnetic anomalies in the Martian crust by the magnetometer on the Mars Global Surveyor, MGS. While the spacecraft traversed the planet at altitudes below 120 kilometers. The magnetometer was initially developed for the Mars Observer, a substantial vehicle intended to operate above 350 kilometers. Thus, it would have been incapable of detecting anomalies. Following the loss of Mars Observer in 1993, a redundant magnetometer was installed on MGS, a smaller probe designed to orbit Mars at minimal altitudes to utilize upper air resistance, aerobraking, facilitating the detection of magnetic fields. Nevertheless, the narrative did not conclude at that point. MGS had to execute a progressive braking maneuver because of damage to one of the solar panel supports. We augmented the frequency of low-altitude sweeps to thoroughly map all anomalies. Following the completion of the 2 Viking missions in 1976, 17 years ensued until another American spacecraft, Mars Observer, embarked on its journey to the Red Planet in September 1992. During this interval, NASA redirected its attention from Mars to Venus, launching Pioneer Venus in 1978 and Magellan in 1989, while also exploring Jupiter and the other gas giants through the Voyager mission in 1977 and the Galileo mission, which spanned 14 years from 1996 to 2010. Throughout this time frame, NASA initiated the launch of at least 11 American rockets directed at Mars. The latest addition is the Mars Reconnaissance Orbiter, equipped with an ultra-high-resolution camera, high-C, 30-60 cm pixel, a wide-angle color camera, MARCL, and an imaging spectrometer, CRLSM, akin to Omega on Mars Express, yet boasting a spatial resolution at least tenfold superior, 20 to 30 m per pixel. The Mars Climate Sounder, MCS, analyzes atmospheric temperatures, water, clouds, and aerosols. The Shared radar probes the underlying structure to a shallower depth than the Mars LS radar on Mars Express. However, it has a superior vertical resolution. The two probes, launched in 1996, accomplished and exceeded their goals. Specifically, MGS operated for over 10 years, with communication ceasing on November 2, 2006. Amid the excitement, a new initiative was developed. An orbiter and a tiny lander would be dispatched to Mars every 26 months during each launch window. The initial missions were the Mars Climate Orbiter, MCO, and Mars Polar Lander, MPL, in 1998. Furthermore, NASA determined that beginning in 2003, the investigation of Mars will be enhanced by an ambitious initiative to return samples from the planet to Earth in partnership with France and Italy. Unfortunately, the entire initiative disintegrated in 1999. All four probes launched the previous year, MCO, MPL, and the two soil-penetrating microprobes, failed consecutively. The Mars program encountered difficulties once more. NASA deferred its sample return initiative until 2015-2020 to focus on a more advanced exploration mission. Nevertheless, the momentum persisted, and following Mars Odyssey's orbital insertion in October 2001, the remarkable achievements of the two Mars rovers deployed on its surface in 2004 reinstated NASA's prestige. See next page. We now anticipate findings from the super-satellite Mars Reconnaissance Orbiter, which entered Mars orbit on March 10, 2006, the Phoenix Lander, 2007, and the Mars Science Laboratory, 2009. Spirit and Opportunity, Martian rovers. The Mars Climate Orbiter and Mars Polar Lander missions had significant failures in late 1999, resulting in a substantial setback for NASA's exploration program. Notwithstanding this, the crew persevered. In June 2003, they required a project that was both secure and remarkable for the forthcoming opportunity. In July 2000, a resolution was introduced: the Mars rovers. The established Pathfinder landing system was intended for deployment. Instead, a mobile vehicle capable of traversing several kilometers is presently exploring Mars, equipped with certain scientific instruments designed for the 2001 lander. Two identical rovers were to be dispatched to Mars using distinct launch vehicles to enhance the likelihood of success. The issue was that NASA's Jet Propulsion Laboratory had merely 3 years to execute missions of unparalleled complexity. JPL faced multiple hurdles, including altering airbags and parachutes, and finalizing a feasible design at the last minute. Each test of the rover revealed one additional malfunction. A fatigued team observed the launches of the two rovers on June 10th and July 7th, 2003. We prayed for the car's secure arrival at their designated location. Could they last for 90 days, their intended duration of labor on Mars? They exceeded even the most optimistic projections. And as of this writing, over 3.5 years, post-landing Spirit and Opportunity remain active, having traversed more than 7 and 11 kilometers respectively. They have investigated the crater floors and ascended mountains, and most significantly, uncovered the unforeseen geology of 2 distinct locations on Mars, where indications of the historical presence of liquid water abound. Spirit was the inaugural rover in the Gusev crater on January 3, 2004. All proceeded seamlessly until the 18th day, when Spirit became mute. The onboard computer was intermittently activating and deactivating, depleting the batteries. After several days of apprehension and technical proficiency, the team effectively rectified the issue, enabling them to concentrate on the successful landing of Opportunity on January 25th. Fortunately, Opportunity alighted within a little crater, exposing sedimentary bedrock for the first time. Due to its remarkable location, Opportunity became the favored rover among researchers for an extended period. Nonetheless, it also encountered challenges. In the spring of 2005, it remained ensnared in a minor dune for 5 weeks, while Spirit regained prominence by ascending the Columbia Hills, achieving an elevation increase of over 100 meters. Partially in reverse, due to a malfunctioning wheel. The objective was to uncover progressively perplexing varieties of sedimentary rocks, elucidating the unforeseen geology of 2 distinct locations on Mars. In 2003, Europe launched a probe into Martian orbit, incorporating bolt-ons and partnering on missions coordinated by the 2 countries. The former Soviet Union in particular adopted European instrumentation for Phobos 1, Phobos 2, and, notably, Mars 96. Nonetheless, the partial malfunction of Phobos 2 in 1989, the loss of Phobos 1, and the failure of Mars 96 in November 1996 during launch prompted a consensus. European equipment would subsequently be deployed on European missions. Following the Mars 96 catastrophe, France and Germany conducted a feasibility assessment for a tiny satellite with sensors analogous to those of Mars 96. The ESA instantly adopted this concept, rapidly formulating a new mission: Mars Express. On June 2, 2003, the European Space Agency launched Mars Express. On Christmas night of that year, it successfully entered Mars orbit. The Mars Express team comprises scientists of several nationalities from throughout Europe, including French, Italian, German, and Swedish individuals. They engage in vigorous discussions over mission objectives, observation techniques, and resource allocation. However, operations proceed smoothly. Through its advanced instrumentation, Mars Express has transformed numerous aspects of Martian research, exemplifying the efficacy of international cooperation in space exploration. The European Space Agency, ESA, has operated since the mid-1960s. Initially, emphasis was placed on astronomical missions and the investigation of the Earth's ionizing environment. But in the 1980s, Europe shifted its focus towards solar system exploration. In 1986, Giotto encountered Comet Halley, and on January 14, 2005, Huygens successfully arrived on Titan, a moon of Saturn. Concurrently, Mars and the other terrestrial planets, Venus and Mercury, appeared to be comparatively overlooked. European planetary scientists relied on Marseless to probe the planet's subsurface, to identify the existence of ancient, concealed craters, depicted here as subtle white curves with the white line at the top indicating the surface itself. The deployment of these antennae was noteworthy. Initially folded in an accordion fashion, the antennae were set to stretch upon the probe's arrival in Mars orbit in April 2004. The procedure was aborted at the last moment, as updated estimates indicated that the deployment could result in the antennae colliding and potentially damaging the spacecraft. In early May 2005, a year later, meticulous computer simulations of the maneuver successfully liberated the initial segment. Although the probe encountered no major problems, the antenna's tip remained disengaged from its designated position. Subsequent investigations were mandated. The findings indicated that it was essential to heat the antennae through solar exposure, and on June 17, 2005, the extension of the 3 booms was ultimately accomplished. For Mars Express, a British team constructed Beagle 2, a compact 30-kilogram module. The Beagle 2 design entailed entering the Martian atmosphere, landing, and analyzing surface materials with small sensors. Charles Darwin, the progenitor of evolutionary theory, completed his apprenticeship as a naturalist on the original Beagle. Unfortunately, after a successful cast-off, Beagle 2 ceased communication, prompting the conclusion that it had encountered a crash. The small vessel had garnered a notable following in Britain, making her demise a source of disappointment for many. The precise cause remains unidentified. Buoyed by their success with Mars Express, the Europeans aim to broaden their aspirations. Mars will undergo additional exploration under the new Aurora program, established after 2005. The creators of Aurora recognized that eventually, Martian studies could transcend basic scientific inquiry and embrace new frontiers with human participation in exploration. Consequently, they incorporated experts proficient in ESA astronautics and the International Space Station into the initiative and utilized relevant resources. Aurora. In several decades, astronauts may discover the frozen robotic emissary from the inaugural Aurora program mission, ExoMars. If a European astronaut participates, the event will symbolically affirm the program's success. The program seeks to advance Europe's exploration of Mars with robotic probes until 2020. The goal is to engage in a multinational human exploration of the Earth. Another progeny of Mars Express, Venus Express. In 2001, the European Space Agency, ESA, contemplated utilizing the technology previously created for Mars Express to construct a comparable spacecraft at significantly reduced expense. What mission will this spacecraft execute? Consultations were conducted among the scientific community, and one proposal emerged prominently. Why not dispatch Mars Express Mark II, equipped with nearly identical instruments, to Earth's neighboring planet, Venus? Venus Express was developed in an unprecedented time frame and successfully launched on November 9, 2005. ExoMars. The Aurora program seeks to cultivate the requisite expertise and technologies for extensive future exploration of Mars. In 2013, the initial phase will involve the landing and deploying a rover named ExoMars on Mars. The aims will encompass technological and scientific pursuits, the quest for evidence of ancient life and examining the planet's habitability progression. The rover will be equipped with a drill capable of penetrating several meters to access rocks and soils unaltered by surface processes. Exobiologists aim to discover chemical indicators of early Martian life within these samples, utilizing a specialized transportable laboratory for analysis. ExoMars will employ a radar instrument to navigate the drill and identify geological strata and ice deposits. Another objective of ExoMars is to investigate the history of Mars's habitability, to enhance comprehension of the environment that future Martian humans would encounter. The rover may be accompanied to the surface by a compact geophysical and environmental apparatus known as GEP, which is affixed to the descent module and has been functional for several years. This could be the initial component in a network of such stations on Mars. Cutting-edge detectors, such as seismometers capable of identifying potential Mars quakes, will examine the planet's present geological activity for the first time. ExoMars may fulfill a long-standing aspiration for exobiologists who were disheartened by Viking's unfavorable outcomes 3 decades before, and geophysicists who recall the failure of Mars 96 and the subsequent abandonment of Mars initiatives by the USA and Europe. They now anticipate the Aurora expedition. Mars exhibits geological diversity comparable to that of Earth. In a few years after the comprehensive structure of Mars has been mapped, examining this geological diversity will emerge as the primary challenge in the ongoing scientific investigation of Mars. Colonies of biomorphs. What are the methods for expediting Mars exploration? Motivated by the natural environment, NASA's Jet Propulsion Laboratory researchers conceptualize a solution utilizing colonies of biomimetic robotic explorers. These robots may traverse on caterpillar tracks or descend to the surface akin to winged seeds. They interact with one another, spread to explore the planet and regroup in strength if alerted to a spot of scientific significance. The success will hinge on the quantity and mobility of the utilized probes. To thoroughly investigate the Martian surface and its subsurface, they must excavate, navigate aerially, traverse, and establish communication. They are devising multiple initiatives that resemble science fiction. Excavating through sand and ice. The Martian surface, subjected to ultraviolet radiation and a chemically hostile atmosphere, is not conducive to detecting original remnants of old sedimentary processes or identifying organic components. Excavation is necessary. Consequently, the European Mars Express mission 2004 was equipped with a mole affixed to its lander, Beagle 2, to investigate the uppermost meter of the surface. The mole, weighing under 1 kilogram, could traverse a sandy terrain at a velocity of 1 centimeter every 6 seconds, propelled by a spring mechanism. Upon securely collecting its sample, Beagle 2 would have retracted the 3 meters of cable, retrieving the mole and its sample, after which analysis would commence. After Beagle's failure, NASA and ESA developed drilling technology for post-2010 missions, such as ExoMars, see prior pages. This subsequent mission will offer a second chance for the tethered mole technology, facilitating the deployment of instruments intended to monitor planetary surface heat flow on Mars for the first time. The polar caps on Mars and Earth serve as climate archives for their respective planets. The cryobot, a robot engineered to penetrate several meters of ice, is presently under development at the Jet Propulsion Laboratory, JPL, in California. Its objective would be to examine the distinct strata of ice as it encounters them, soaring and drifting in the atmosphere. An airplane must either go 5 times faster than it does in Earth's environment, or possess larger wings to fly through the Martian atmosphere. The gravitational force of Mars is 2.7 times weaker than Earth's, and its airlift is around 100 times diminished. NASA engineers, rather than conceding defeat, have created multiple prototypes. One of these is Ares, an aircraft with a wingspan of around 5 meters, which may eventually traverse the Martian atmosphere at an altitude of 1.5 kilometers, capturing comprehensive photographs of Valles Marineris, or profiling magnetic anomalies at unparalleled resolutions. Helium balloons represent an alternative option. A balloon manufactured in France was intended for the Russian Mars 98 mission. However, reductions in the Russian space program necessitated the abandonment of the plan. Proposed Mars aircraft. Due to the low density of the Martian atmosphere, such an aircraft must be exceptionally lightweight, possess an energy source, and be capable of mid-air deployment. Exploratory balloon. The French space agency, CNES, built a balloon for the aborted Russian Mars 98 mission. The balloon contained 6,000 mm3 of helium within a cylindrical structure measuring 45 meters in height and 12 millimeters in diameter, constructed from 6 micrometer thick mylar film. The total weight was 60 kilos, comprising a 30 kilon scientific payload and a 30 kilon balloon. The absence of buoyancy during frigid Martian nights, shown by the black band in the figure, results in the balloon trailing its serpentine ballast line, guide rope, around the surface. The wire would have functioned as an antenna, conducting radar soundings on subsurface materials. After obtaining lunar samples in 1969 and throughout the 1970s, refer to table, space agencies have recently contemplated ambitious initiatives to retrieve samples from additional celestial bodies within the solar system. The Genesis expedition by NASA collected solar wind samples despite the spacecraft crashing upon its return. The Japanese Hayabusa mission, ISAS Japan, successfully landed on the asteroid Itokawa and is currently confronting a difficult return voyage to Earth due to the malfunction of several spacecraft subsystems. The NASA Stardust mission successfully retrieved dust from Comet Wild 2 on January 15, 2006. When is the launch date for the Mars sampler? The return presents a technological difficulty. The gravitational force on Mars is double that of the Moon. A launch velocity of 3.5 km/s enables insertion into a low orbit, while a further 1.5 km/s facilitates escape into space. One proposal involves using a tiny rocket to launch samples into orbit, accompanied by a second component, a satellite equipped for maneuvering to rendezvous with the rocket and return the samples to Earth. All these tasks will necessitate substantial fuel consumption. Will more fuel-efficient methods, such as electric propulsion and aerocapture, be utilized to initially place the satellite into orbit? NASA may restrict the initial Martian samples to air substances and dust gathered during a swift flyby of the planet. The SCLM mission by NASA, originally slated for a 2007 launch, eventually did not receive confirmation. Hazardous specimens? Martian samples will be analyzed in a restricted number of high-security laboratories, within sterile chambers similar to the one seen, which houses lunar material retrieved in 1972 by the Apollo 17 astronauts. This approach safeguards the samples against terrestrial contamination and guarantees they are isolated sufficiently to confirm the absence of potentially hazardous Martian life forms. These additional samples would initially be collected from the planet's surface, whereas the SNC meteorites have likely been expelled from the deeper layers of the crust. Recent samples indicate that the surface material has altered due to climatic conditions, hydrological influences, sedimentation, and hydrothermal processes. They may even bear remnants of any primordial life on Mars. Furthermore, they would have been safeguarded against any terrestrial contamination. The primary inquiry for scientists is the type of samples to target. What is the subject of their investigation? To ascertain the chronology of Mars, it would be advantageous to obtain samples from a location where lava has traversed. The only existing technique for determining relative chronologies is the enumeration of meteoritic impact craters, which lacks precision. Seek evidence of life. A location characterized by sedimentation or an ancient riverbed is optimal. Why not excavate one of the polar caps, which retains a record of Mars paleoclimates? We will necessitate several samples and an adequate number of spaceflights to procure them. The sample missions scheduled for the years after 2015 will likely be complex and highly demanding. Several launches will be required, with each mission potentially exceeding €2 billion in cost. NASA, the program's initiator, would find it challenging to finance it independently, particularly if it persists in advocating for the return of American astronauts to the Moon before 2020. With robust support from the scientific community, Europe may eventually assume a significant role in this new initiative and take the lead. The continuation of the ESA Aurora program beyond ExoMars will hinge on the political commitment of European governments to pursue space exploration. Mars is the sole celestial body in our solar system currently deemed viable for potential human exploration, while Venus, our other neighboring planet, presents a deadly environment. Nonetheless, significant issues remain to be addressed. The challenge of transporting the requisite fuel for the return voyage emerges. A journey from Earth to Mars would be only marginally more costly in fuel than a journey to the Moon, particularly since the Martian atmosphere can decelerate the spacecraft's fall, unlike the Moon. Nevertheless, returning to Earth from the Martian surface, whose gravity is more substantial than the Moon's, would necessitate additional fuel. Additionally, there is the contentious issue of the duration required for travel to Mars. Employing conventional propulsion techniques, each interplanetary mission would necessitate a minimum of 6 months. We must also consider the duration astronauts spend on Mars. Upon landing, astronauts must await the subsequent launch window, determined by the relative locations of Mars and Earth, to commence their return voyage. In the majority of cases, and this indicates approximately 500 days on Mars, a round voyage to Mars would need over 2 years. The vehicles doing such travels must be durable and equipped with systems to recycle water and oxygen for the crew's needs. Crew members will encounter elevated amounts of cosmic radiation and solar wind, posing a danger of cancer, while the lack of gravity will progressively impair their physical capacities over time. Consequently, initial initiatives were monumental in magnitude. In 1952, Wernher von Braun, the architect of the Apollo program, envisioned a fleet of spacecraft weighing tens of thousands of tons. In 1989, President George H.W. Bush pledged to the United States an extensive initiative to construct massive spacecraft exceeding 1,000 tons in Earth orbit, utilizing groundbreaking technologies for propulsion. The projected expense would have been no less than $500 billion. Engineers have subsequently devised more nuanced and realistic designs, which NASA has included in their reference mission. These advancements render the prospect of transporting astronauts to Mars technologically viable. Despite the project's significant expense, it will adhere to NASA's budget, particularly if additional countries provide support. Similar to the Moon program of the 1960s, scientific research cannot substantiate such expenditure. Notwithstanding many challenges, traveling to Mars might present limitless opportunities for exploration, research, and comprehension of an alternate universe. Will individuals traverse Mars in the forthcoming decades? In January 2004, President George W. Bush formally tasked NASA with this long-term target, although his first aim was not Mars, but establishing lunar bases by 2020. The initial phase necessitates the creation of robust launch vehicles and life support systems akin to those required for a Mars mission, albeit with the potential consequence of delaying our inaugural presence on Mars even more. De Vaucouleurs provided a comprehensive analysis of all existing observations of Mars, utilizing the most advanced understanding of planetary physics to summarize established knowledge derived from thorough examination. 52 years post-publication, the book proved enlightening as nearly all its content was erroneous. It is stated that the permanent atmosphere of Mars consists solely of nitrogen and a minor amount of argon, while it is now understood that the Martian atmosphere is predominantly carbon dioxide. De Vaucouleurs estimates the surface pressure on Mars to range from 85 to 8 millibars, with the actual value approximating 6 millibars. The author states in a footnote, "We can now confirm that the polar caps resemble those on Earth, composed of frozen water." They further assert, "We shall not dwell on a comprehensive examination of the reasons why the hypothesis concerning frozen carbon dioxide is no longer viable. Indeed, the caps contain a significant amount of carbon dioxide snow." Instead of ridiculing this esteemed author, we recognize that the challenges posed by Mars for the most eminent scientists in history provide a valuable lesson for us now. Direct measurements have been obtained from the Martian surface, and advanced remote sensing sensors comprehensively map the planet from several perspectives. Despite the implications of the title of this book, and although we have endeavored to consolidate existing knowledge, we remain somewhat distant from conveying the true narrative of Mars. The sole certainty is that our book will be a topic of contention within less than 3 years between the initial and present versions. Findings from Mars Express and the Mars rovers have necessitated the complete revision of some sections. Undoubtedly, time will refute several theories presented below. Are we exhibiting pessimism? We are not at all pessimistic. This book encourages your engagement in an exhilarating scientific and technical expedition to investigate the Red Planet and uncover its origins and processes. We aspire to have effectively communicated the marvels that Mars continues to present through ongoing discoveries and revelations.